Okay, welcome everyone at the 2019 RoboCup Workshop in Eindhoven, hosted by Tech United. This is the beginning of the live stream. Zet hem aan.
dan kom jij en dan leg ik het programma uit. Okay, hi everybody and welcome to the MSL Workshop 2019. Welcome in Eindhoven to all those teams that traveled from far. My name is Ense. I'm the new team leader of Tech United. I'm the successor of Wouter. I hope you all know him. Today I'm going to give you a bit of an introduction in the planning of the MSL Workshop. But first of all, I want to give the word to René van der Molengraaf to give you the official opening of the MSL Workshop 2019.
Thanks, Ense. So, this was the official opening, I guess. Welcome. The ninth workshop started in 2008. At that time we had in Kassel first workshop with the German teams that we had at that time. Very good teams like Tribals, Cops,
We are now here with 7 representatives of 7 teams, partly completely different teams, which is great because it also shows that we are developing as a league. Hopefully we will have 3 days of nice discussions, a lot of new ideas, questions. We can basically share knowledge with each other. So other years this has happened, so I'm not doubting that will happen this year. Of course, you already had now, for the people who were here in Eindhoven for the first time, the Dutch croquette during lunchtime, and later on we will have a more oriental style buffet dinner in the evening, and now I've been there a few times, so I think that will also be okay. Let's start, but not before I've asked you to give a big round of applause, and I mean a big round of applause, for the real organizers, Ense, Robert and Wouter. Wouter, where are you? Ense, back to you.
Okay. In front of you, you can see a little paper. I saw a lot of you have already observed it. In the front page, there's a little welcome to you, participants of the workshop. And on the back side of the paper, there are 2 components. First is the program, which you can also see here on the slides. We will start with team presentations of each team. The idea is to do a few presentations of 20 minutes with 5 minutes of questions. Here you can see the order. And in between we have a couple breaks for coffee and tea, which you can find on that side of the room. On the other half of the back side is a little place to write your name. You can fold the piece in half, and then you can present it in front of your desk. And that way we can all see what is your name and which team are you from. So without further ado, let's start with the first team presentations of the Falcons.
Op die witte hadden we hem gezet. Je hebt die witte, die andere. Ja. Okay, thank you. And also thank you Tech United for hosting us here. If that's better, but I don't think. Oh, the live stream. Okay, sorry. Yeah, Falcons team presentations. For the ones that don't know me, I'm Ronald van der Weijden. I'm part of the Falcons already from the beginning. I'm the team captain as from Sydney on. So Jaap Vos was the former team captain, and I took over from Jaap since July. Jaap is still involved in the team, so you will see him also on the tournaments probably. What are we want to talk about in this presentation? A little bit of general stuff, looking backwards from the season 2018-2019. Then Stan will tell a little bit about our new hardware platform. And then Jan, Erik, and I don't know Jan Erik will have a talk about software usability, diagnostics, and then we'll come as a vision system. So, what has happened with the Falcons in 2018-2019? Now, we introduced a new proto for our robot. We started with we saw the overalls needed to be faster and all kinds of stuff, and we need to have a new platform on that. So we are starting to build a new platform. That was Robot 7. We already played a game in Portugal this year with Robot 7. Unfortunately, we didn't manage to play the game in Sydney.
Can I for a second, could you put the microphone a bit closer for the side?
So better?
Yes,
Yeah. He's giving us some more information for our new platform, so we are happy that we did introduce it. Next to that, we for the first time in our team we introduced an extendable keeper frame. So we saw already the results in Portugal and in Sydney. So with less goals against as in the tournament, so that's also a good thing. Next to that, of course, the results of the both tournaments, the third place in RoboCup and the third place in Sydney. What we see that is our robot uptime on the tournament is very high. We have almost always all robots on the field. That's a huge thing for us. That will help us, of course, also for having good games. After Sydney, we came back. We had some nice things within HML. The communications department within HML did some great things on having information about the Sydney tournament. And it resulted in a huge increase of manpower that we are having now. So before Sydney we were with 70 people, and now we grow already to 46, and still people are coming in from all kinds of departments within HML. It's for software, from hardware, but also logistics and all kinds of stuff. Next to that, we created a new organization structure. What we saw before is we were in one big organization, big 17 person, but now we created a lot of new subgroups which were working naturally in natural teams towards to Bordeaux, so the next World Championships in June. All these separate teams have 4 to 9 people in there, and are working on a lot of stuff, both hardware, both software, but also on promotion, communication, and all kinds of stuff. This is a little bit over a poster that we created of the things that we want to do towards Bordeaux. And I will give the word to Jan, I think. To Stan, sorry, to introduce a little bit about the hardware.
Thank you. As Ronald already said, this year we introduced our new Robot 7 to come up to improve our performance. And in the picture you could clearly see it was based on our old robot, and we didn't change the frame, we just put the hardware on little different places. We found out that was very useful information, but it was not the big step we want to make, because we had some more problems. For example, the bottom frame was not stiff enough, and that moved over time, so therefore all our calibrations went off. We introduced more vibrations in the system. So therefore we went to a fully redesign and tried to change as much things as we thought was needed. So here we see an overview of it. Most important thing, we stay with the 3 wheels. We don't go to 4 or something else, we stay with it. We keep the same motion as is being tested on Robot 7, except for that we will change to new motors, but I'll come to that later. And also the serviceability is one of the key points where we want to improve on, that we can service as much with removing as little parts as possible, or if we need to remove parts, that they are easy to remove and easy to mount back. And very important, our goal is to have 1 robot in Portugal again for testing, to prove that it's working before we go to a full team of it. We go a little bit towards the Kambara design, and having a bottom frame designed for all the heavy components. We still have the same batteries as we had in the old system, but we moved to new motors. Here they are a little bit smaller, but they are more powerful, so that we can have more traction on the system, on the ground, because in the calculations it showed that we were running already at the end of what the motor could, and we were already in overusing it, and to go even more that would probably break motors. So therefore we went to a more powerful motor with more, so we have more spare to go to increase the speed in the future and acceleration. Also, in the ball handles you can see already they're slightly different. Come back to that in the next slide. And then the bottom part is covered by the blue plate, also for stiffness, to prevent that the bottom part starts to bend. And very important, we moved from 2 wheels to 3 wheels per motor to have more grip on the field. Above that one, we want to make 1 plate for all the service and electronic parts. So this will be mounted with all the electronic components. It will hold all the cables, and the idea is that if we need to do something, we can access it from the bottom, or we can take off this plate very easily to reach the motor compartment and the things inside. As you can see, there's a lot of electronics on it. Basically every electronic part is being redesigned, and that's in progress right now. And then we will have 3 carbon tubes to hold the motor, hold the camera SC up, so that we have less weight. In the end, the robot will not be much lighter as we are now, but everything that we can gain is useful. And also it brings the center of gravity down, so it will be more stable. Then on the new ball handling system, we are trying to introduce some damping, and that's also what we like to have some feedback on what other teams already tried. Also here we want to go to a more powerful motor to have more grip of the ball, because we were already really at the end of what the motor could handle before braking. And we moved to a different kind of sensor, because the one we have now is very unlinear, and for good control we want to have a linear sensor. So that's mounted now on the axle as well. And then I give it to Jan or to Erik.
Thank you. So a little bit on the software. We focused actually on just 2 topics this time. Some things that we were working on last year. Obviously software doesn't have the sexy pictures that we had for hardware, but I'll do my best. The first one in the usability. We were inspired by VDL, who are actually doing some promotional work for, well, giving it at schools, making, promoting technique for at schools, at kids. And we saw that it is way too difficult to demonstrate anything from our robot, because we obviously program mostly for just playing a match and not actually being able to test separate things. So we worked on making these blocks. Google Blockly has a nice library that just allows you to make blocks, and they support the graphical user interface and how to make the blocks. And all you have to do is plug in what code it provides. So basically the only thing it does is, if you make these blocks, specify them up front, you drag and drop them in your browser, and it just outputs some code in the browser, and we made sure that that code gets executed on the robot, and that robot then performs this. And this actually allows less technical people that have less knowledge of software be able to, this scenario, to put a robot at a, for example, at the own half penalty spot, and from that point tries to intercept and pass back the ball multiple times. And we do that then, for example, for this one, from both sides of the field, and we can just have the robots pass one to another, but obviously the opportunities are limitless. That's one thing we worked on. Another thing on the diagnostic side, so before I skip to the next slide, most of you that have worked with the robot at some point probably found that something's not working as expected. And then the question is, what is it? And by now the robots, they're the hardware, electronics, software. The software is pretty big, you have a lot of software going on. Where is the problem? Where is it not functioning as expected? So then the question is, how do you pinpoint where the problem is? And that can be very tedious and cost a lot of time to pinpoint what the root cause is. As I said, the first point, not behaving as expected. How do you pinpoint the root cause? What we've been working on is taking RTDB to a little bit to the next level, in the sense that we create RDL files, which is what we call them RTDB data logging. It's basically a full timeline of all the data written to RTDB. So it's like we can play back that whole data like a match. And in that, it has all the data that the robot was publishing and or reading from RTDB database. And here is just a screenshot from our top, which is just showing what is currently in the database. And as you can see under age, it's only a few milliseconds, so it's constantly publishing new data. The RTOP that you see here was already provided by Kambara when they made RTDB. We made the RDL file such that we can play back it, and we do the playback in our own visualizer. And what we added this year is that we added a camera on top of the field. We played a match, and we were able to project that video in our visualizer. And here we actually see the images from the match that we played against VDL, and we show the positions of the team members where they are thinking they are versus the actual video. And this is actually the first time that we are able to show the ground truth compared to what the world model is thinking of the robot. Also, we see here the ball is, well, almost there, and it has a specific vector, and based on the velocity of the ball, this vector gets larger or smaller. We see, for example, here for robot 3, he decides he should actually move to over there. If we have obstacle avoidance, he's trying to avoid someone. We also get a sub-target saying, wait, actually go around someone. And this has already shown some insights why some things were happening. But this is not everything, because still, if you say, hey, we're making the wrong decision, why? That can be quite interesting to figure out in your tactics software. Why is the robot making the wrong decision? For that, we introduced tracing, and in every part of the software we added a call doing tracing, writing tracing to a buffer, and that is every tick being stored. And here we see actually so they call this a flame graph. It's basically, if you look at this one, we have one function that executes the entire tick of all the decisions that we make. And I can click on any one of those decisions. And every decision I click on, I can get the data like this, showing where in the code this decision was taken, and which tree was being traversed, and which decision was taken. Like, for example, here, does a robot have ball? True or false? And based on that, we can actually look in our behavior trees. If you may recall from our other presentations, we can look at what decision was made. And this data is being written by every robot for every single decision being made at all times. So everything that the robot is thinking during the entire match, we can play it back and zoom in on a specific scenario or decision being made. So everything is being stored. Right? And that's this data. So on the base station, we receive the shared data from RTDB. So that's only the higher level and more important data that the other robots should know. That's the high level playback that we can do. And if we're really zooming into, hey, that robot was making the wrong decision, then we can actually take the data from the robot, because everything is being stored at all times. And we can actually replay what he was thinking in the local and the shared data, and then zoom in on the software tracing to see what decision was being made and why, and then maybe fix it. And I believe, yes, that was the part on the usability and diagnostics. Yep.
Yeah. So the last topic of our team presentation was on request of the other teams in preparation of this workshop about how we achieve omnivision using our new multicam system. Oh, forward. A bit of an introduction to our multicam system. It's an assembly of 4 cameras pointing in the 4 directions, supported with some hardware, and the specs. I have a backup slide on that if you're interested in the PDF for later. And one of the cameras sees something like this: 600 times 800 pixels, slightly more than 90 degrees horizontal, so it completely covers its surroundings, and pretty high vertically, 130 degrees. But of course with the large fisheye distortion. You can see our hole. Those beams at the top are straight in reality, and here they are quite curved. How do we do localization with the system? It involves a bit of calibration, just calibrating the fisheye distortion of each camera, but then effectively, stitching is maybe not the best word, but okay, aligning the cameras to each other, the calibration system, we just take some landmarks which are on the border of two cameras overlapping, and by calibrating that in, you make them compatible. This is all quite robust, actually, we found, using some standard functions provided by the OpenCV3 library. Then more about the software details for localization. The line point detection yields white pixels, which are transformed to the robot coordinate system. We just use a lookup table for speed, which we calculate up front. And and since already earlier for the OmniVision system, we use a simplex method to fit the position using those pixels. And the result is plotted in this right bottom plot. And you can see that, so here is a transition from two cameras, so pixels are continuous. This is 7 meters distance, so that's a verification check for us that the calibration is good enough. Although you can see that the density is of course pretty low so far away, the robot standing here. And for the rest, so Vision provides the candidates, and World Model selects the proper candidates, takes care of this, the symmetry. And that's actually an architectural principle we use for all our Vision, for all our software, also for balls and obstacles. Vision provides the candidates, World Model does the filtering and the stabilization of the data. So I hope that answers the question about how we achieve OmniVision. It's a bit interpretable. If not, ask us later. Then maybe I can add some more to this. Finally, there was also a question about machine learning. Our view on this is that we see two candidates, one being the action making, we call this team play in our software, decision making, and the other is computer vision. For the coming time, we choose to focus on machine learning in the context of vision, not the team play. Because for us, the team play is a bit like deterministic and sort of simple, and we like to keep it that way, and we are a bit afraid the side of the practical problems of tuning or of the learning effort that we will sacrifice some insight and diagnostics capabilities, as Erik also mentioned. So, but for this year we plan to experiment, integrate maybe already machine learning mainly for ball and obstacle detection. The black and white balls are of course a big challenge, which with the current filtering software we have is not doable. And also the obstacles are quite tricky. That's where we hope to show some progress this year. Yeah, that was the end. I think it's time, 5 minutes time for questions. René.
In the new hardware design, there was still this pyramid tower with the camera on top. So why not leave that out and move the cameras around the lower shell of the robot? Your center of gravity would be lower, and I think the whole stability of the platform is bigger than take off those two guns, just remove them all together. And
okay.
Given that you have these cameras for OmniVision, you could also put them on the platform itself, right? Did you consider that, or did you deliberately choose not to do that?
I think we did. Yeah. You want to take it?
Yeah. We didn't. For the question, it was then why did we not change the camera, and why do we keep it up and don't mount it in the frame? The reason we didn't really consider changing it because we're already changing so many parts, and we're already a little bit afraid we have limited manpower, so we choose to. Yes, but they are from the hardware development. They are not that many.
Best have the camera as high as possible, otherwise you can't really see.
That's also the main reason I would bring.
Yep.
But if you're really low on the field, then you.
most of the time the ball is on the floor, and it's nice to have a bit of an angle to seeing it from top. Then you rely less on the stereo with other robots. Oh yeah, indeed. You would also sacrifice some white pixel proximity there. Yeah. Well, we can. There's not so much mass in there, I think. How heavy is this top assembly, including the beams? That's not going to be more than a kilo or two. So half kilo?
I think it's about a kilogram, but that's a guess. I never measured it.
I'm trying already for weeks to lose a kilo or two. I can tell you it's a lot.
But here is 35, huh? Headbutting. Headbutting, yeah. But thanks for it's an interesting idea.
No, yeah, the whole point that we saw this design pattern of having this camera at 70 centimeters was because of the rule that we could make it stand higher. Otherwise, we would have, of course, because we want to have nice options. But yeah, now you show, actually shown that there is technology to do it differently. So I think I would rather have a platform that's really low on the floor, and still have this omni vision, but in a different way.
But it's interesting that you say, actually the question comes up, why do you want to be high? And the answer is formulated as because you want to see how far something is. But if you have another way to determine how far something is, you don't need to be high.
No, then.
So if you have stereo vision or so, it would reach the same effect maybe.
Yeah. But okay, we could consider it, but it's definitely not in this iteration, I think.
Even as low as the ball, even the ball blocks exist. And now you look over the ball and see behind it.
Yeah, that's a nice thing. If you know what is blocking, you know where the ball is.
It's about what's behind the ball. Can you see behind the ball if you're really low? Looking for it.
But you have five players, so that's really out there.
I want to see as much as possible.
And if you put the cameras some more than the width of the ball apart, you can see behind the ball.
You never play with one robot, right? Could be isolated.
Let's maybe move on.
Next question.
Any other questions? Yeah, Wouter.
Yeah, so for logging your data, you have basically two frameworks, right?
Yeah.
And the second one was about all the decision making.
Tracing, yeah, we call this.
So, it must be an enormous amount of data, right?
It's quite a lot. It's way more than what we have in the RTB in the data logging.
So how do you fastly identify where the problem might be?
That's what you typically start with. Yeah? With the standard playback, you find your timestamp of the problem and the components which are suspect. And then you choose to, on that timestamp, you find the corresponding data. And you can get a timeline there, which you can zoom, scroll, zoom in to the right timestamp for that specific component. You want to follow the data stack. So we always start typically with the robot data logging to find the timestamp exactly, and then drill down in the tracing.
So
does that answer?
Those important decisions on your other framework.
Oh, sorry?
So you have apparently the decisions logged in this framework.
Well, decisions of robots are also in the robot data logging, so then typically you don't need to drill down, but sometimes you do.
But can't you map it directly into the other framework?
Well, the final result of this whole tree is like we take this action, and that action gets logged also in RTB. But how we got to that action, that is in this whole logging.
And so I'm wondering why it should be split. I mean, in the end, you can fuse the data, right?
Putting all this data in RTB, then we wouldn't fit in the bandwidth.
Okay.
Can you explain what this looks like in the code? What you need to do, what you need to add to the code to integrate this?
Single line.
Yeah.
Per function.
Yeah, so
It's like printf. It's like printf, but then trace. And then on the background, it's written to a memory buffer. That's all thanks to this this framework we use. And then it's flushed to the files or to the file system sometimes. So it's basically printf on fire.
So now this trace function will log a lot of the details about the decision making. Well, what if I would like to do time profiling, for instance?
Again, that already is included in here because it also shows execution time function. And also you see on the left one, you see two processes. The top one is team play, make a decision. And below that is actually path planning. So we can see how much time it takes from team play to make the decision to path planning make the decision and then set point to the border.
And you take these decisions every tick,
Yeah.
right? So can you also see between different ticks if they took the same decision and when a decision is changing?
Yeah. You see it very clearly because of the color.
That's hard. I think that's what I would actually prefer the RDL and the tools we built on top of that for, to make a timeline of per tick data. We don't have side of that, but we also have the tools for that.
Often you're interested when something is changing in the well, what it thinks is happening in the world or so. And when it takes a new decision instead of the same decision as last time.
That's a nice one. So in our current playback, we have a timeline and a slider, but we don't yet have like a forward bar with a star for a certain event. That would be some change of state. That could help with this visualization to be able to quickly to the right point in time. Some ideas, we have some ideas on that, but also we want to not make this tool too complex, so we have some other open source also tools for that. AST plot is the one.
All the information is shared or local? All the information shared local in the robot, or so?
Configure which information we want to share for the base stations you imagine, want to see, and the rest is local. And it's typically a bandwidth trade-off argument.
But the question is if I answer correctly, do you log only the shared information from the activity?
On the base station we do. On the robot, however, we log everything. So that's why we have two instances. Logger runs not only on the base station, but also always on the robot.
Yeah, okay.
It's just another instance of the same tool.
Yeah, right.
That extra line of code, is that automated to bring that in code, or do you have to do that by hand?
By hand.
So would that then be the next step to automate that? Because of course there are already compilers and build systems that can do this sort of things automatically.
That is possible, but I'm not sure if it's desired.
Yeah.
Because we handpicked some functions that were really making decision making, so we only get the data where decisions are being made. Otherwise you get all the different functions that you have that you may not even care about.
As a developer, you need to choose which and how you instrument. It's also a lot of a development tool, actually. Yeah? When you're developing something, you want to verify if data traverses properly.
If it was a generic development tool, I would expect to have it in the development environment itself, such as, for instance, in existing commercial systems.
The framework that we're using is actually from Google, and they use it to profile Android.
But we instrument our code manually on the topics, on the components and functions which.
Everywhere, but only on the specific.
Yeah.
That's all work, right?
Yeah. But it's worth it. So.
For all software components.
But you're not flying blind, so. And sometimes you can.
I see the value of it, and also want to have this functionality, but I don't want to have to go through every line of code to determine
Then use maybe a language which can decorate functions for you.
So basically, you also would like to have an automated debug correction system.
Yeah,
so machine learning maybe.
Tell you, but we have that already.
You have that already.
Automated solution.
So any other questions? No.
Okay.
So thank you.
Yes, no problem. Thanks.
Then I'd now like to give the word to Kambada.
To put it like this. It's easier for me. Oh, it looks so small. Okay. Hello everyone. So I guess most of you know me for a while, right? No, yeah. And my presentation, our presentation, will be somehow based on some of the requests that have been sent by other teams, and some extra stuff, and in some ways also it has a kind of timeline regarding the issues that I'm going to tackle here. This is for those that don't know what Kambada means, but it's basically a startup, and our robots, and our overview is presented in this slide. The first point is basically just a teaser. As my grandmother used to say, at my age I already have a dog license, which means that I can do whatever I want, and my boss can pick up what I left behind. In fact, doing this presentation, I feel a little bit like a red fish out of the fishing bowl, because most of the themes are not specifically related to my areas of working. But anyway, we'll focus on some issues regarding machine learning, what and where in terms of Kambada, let's say. Also on team strategy. This will be the main theme, the main theme in the presentation, and also I'll end with some an issue regarding the large data set logging that has some relations with the work that Falcon just presented right now, although we are earlier in terms of phase of what you're moving into, let's say. Okay, motivation, this is a teaser, of course. This is not the motivation. Our motivation is to work as a family towards developing effective cooperative robotics in dynamic environments, okay? But just to present Ronaldo, does anyone knows Ronaldo? Okay. What does it mean? Which one? Yeah. Yeah, that's right. Okay, so moving to machine learning. We don't actually have a lot of experience doing machine learning, despite the fact we had already at least 2 PhDs in our lab related to machine learning, but at least one of them is not related to Kambada, so it's on a different field. But some years ago, we actually made some incursions into use of machine learning for specific behaviors and low level actions, let's say. And our experimental tests basically, and this is like a conclusion, that machine learning may be well suited and easy to use or to train level or low level actions behaviors such as dribbling the ball, holding it, engaging the ball when it's receiving, shooting at the target. Also in vision, of course, for being able to detect certain type of objects on the field. On the other hand, our perception is that if we want to go into the IA level, machine learning for this kind of application may be a little bit hard to tackle and may be inefficient. And this is, of course, I have no actually ground results to support what I'm saying, but it may be inefficient due to the natural dynamic reality that we are facing during the competitions, basically. So I have some doubts regarding the use of machine learning for the high-level software. I will show just two short, very old videos. You will have the opportunity, if you ever or never saw our second generation robots, you will see them in action here. And the idea here is how to learn to get the ball normally in the position where the back of the robot is looking into the opponent goal, then rotate as fast as possible with the ball and shoot at the target. And let's see if this works. Yes, hopefully so. So this is our older robot, which was round and only had a small rotating roll on top as ball holding. Sorry, not what I want to do. Yeah. So this is trial 1, and this is using reinforcement learning. Yeah, it was quite effective, right? So we have a whip, a virtual whip, and there's one whip there. And so moving to trial n plus k, I don't know, we can show you the result with the same robot on the same field. Of course, there's a lot of ball holding. Please don't comment on that. But you can see that he has learned how to turn as fast as possible without losing the ball using that particular grabber. So this is a simple example how low-level actions or behaviors can actually be taught in an environment like this. Sorry? That's a good question. But as I said, I'm a red fish out of my bowl. I'm not quite sure at this point how big it was in. But maybe below, well below 100, I guess. Yeah, well below. But I won't sign under that, okay? So moving to the second theme, team coordination strategy. And the most important tools that we use for managing these aspects. We consider that there are two, of course, a lot more than two, but two key factors to win a match, either in MSL or in other type of competition similar to this one, which are team coordination and strategic position during the game, dynamically, of course. Of course, there are a lot of other issues. We have to be able to shoot strongly with the correct direction, to be able to observe, avoid obstacles, a lot of other stuff. But team coordination and strategic positioning, if we do it effectively and efficiently, is halfway to attain the goal of winning the game, or at least to get a draw by impeding the opponent team to score at our goal, right? So we divided this work into 3 different type of scenarios. There was some previous work related to this. In 2000, Peter Stone proposed a solution called SPAR, Strategic Position with Attraction and Repulsion, in simulation 2D. It was a very simple solution in which each agent had attraction and repulsion coefficients related to other agents and objects on the field. In 2001, Luis Paulo Reis proposed SBSP technique, situation-based strategic positioning, which we actually use in one of our tools. And this basically takes into consideration the area of the field where the ball is, and is particularly useful for set pieces where the ball is stopped, and the relative position of the other robots for a particular situation of the game. In 2005, Dashi proposed this DPVC, which is an extension of this with the dynamic position based on Voronoi cells. using attraction vectors among the different elements on the field and on the game conditions. And this Delaunay triangulation was proposed in 2007 by Hakiyama, and I present this Delaunay triangulation because we also still use something based on this technique to define our organization, let's say formation of the team during the game. So the motivation for selection of one possible approach to tackle the team coordination and strategy was based on this set of points. First, use a spatial representation using grid cells is based on an idea to simplify the world state modeling. Also, we have looked into those articles and noticed that utility functions have been previously used to select a role within multi-agent systems, not necessarily robots. And then in 2004, there was a paper presented by Shemovich that presented what they called utility functions that sends out as a paradigm for dynamic coordination of multiple robots. And what we saw, we started back in 2004 or something like that, in those years, a lot of years ago. And what we saw is that these utility functions could be actually successful, and we started from that point with a similar idea to apply a solution in order to create a solution for coordination and strategic positioning that we called utility maps. I believe that Tech United also used something close to this or similar to this, basically. And so this is somehow historical, let's say, but is also an answer to one of the questions that was posed by other teams that would like to hear about this kind of issues. So this is actually not new, but we are still evolving also on top of this. So just to show a hierarchical static, not functional model of our software structure, we have coordination, which controls or decides roles. Basically, the role that each robot can have is one of these. Maybe we have one or two more under the sleeve, but they are not there. So it can be a goalie, a striker, a defender, a supporter, a replacer or receiver. So you will see some of those names appearing on the next slides. And then the roles will decide, based on a priority scheme, which set of behaviors will be applied to deliver a particular play. So moving into the solution that we adopt, which is the utility maps. To build an utility map, we have to rely on three things. First, a collection of occupancy maps that can include opponents, teammates, and the ball, basically. So an occupancy map gives each robot a global idea about the state of the world around it. We also need field of vision from certain points. It can be from each of the robots, it can be from the ball position, it can be from any point in the field, actually, or from the goal, for instance. And then we need a specific set of conditions that will act as constraints and will determine which occupancy maps and field of views are to be included in the construction of the final utility map. This is exactly an idea of what is a field of view. And it is interesting because I was just looking into this over there when we were discussing about bringing the cameras down. And for instance, in this situation, this is a field of view for robot number 3 that you can see there. And if the ball was in front of here, there is a blue area completely covered because of the ball being obstructing the vision of the robot. By using the camera on top, we don't have that particular situation. So the red area is the areas that this robot can see. The others are somehow covered by obstacles, which are teammates or opponents on the field. So, as I said, what I will present is for strategic coordination and strategic positioning, 3 different scenarios. The first one is defensive set pieces. So whenever there is a free kick or a corner kick or another restarting situation, where the ball belongs to the opponent team. So the main objective in this case is to prevent the opponent from performing a pass, let's say. Of course, that if the opponent makes a pass within the 2 meters distance, there's no way to prevent that. But today, in most of the situations, teams will try to make a long pass because it's much more effective. For doing our utility maps, we start by the Delaunay triangulation tool that we use, and on top of that, we add some extra rules based on the rules of the competition. For instance, the minimum of 3 meters away from the ball. Only one player can be inside the penalty area, in our defensive penalty area, and we add an utility between the ball and the obstacles to cover lines of passes, let's say. The Delaunay triangulation the Delaunay triangulation tool is something like you see here. Actually, you can edit this and add more triangles. Each point, which is a vertex of a triangle, is a set point where we place the ball along the time. And every time, if, for instance, if I place the ball here and press and create, then there will be another 3 triangles created here. And for each of these points, we decide what is the position, the fixed position, static position of our 4 robots. So the goalie will be on the goal, of course, but for the other 4 robots. And then from a particular, we have to do that for all the vertices. And then there is a function that will interpolate and generalize this so that if I place the ball, for instance, inside any point of this triangle, the robots will move between the 3 possible organizations that we set in each point. In that way, we can do or can come out with a solution of performing a team coordinated movement based only on the position of the ball. This, of course, has a huge drawback. Sorry, this is a simple description of what I just said. But there is, of course, one important drawback on using this approach, is that, of course, with this approach, we do not consider the position of opponents. So this is very nice for a show, for demonstrations. I remember we showed this on our, those days were not even called scientific challenge, was free challenge back in 2007. And it was spectacular, of course, with our 4 robots on the field, moving the ball and all of them moving in a coordinated way. Okay, so this is only basically the baseline and a fallback if everything else does not apply, okay? So, then we have what we call height maps. Height maps define priorities, in this case for a particular situation, in this case called cover. Cover means we want to cover lines within the field, let's say. So in these particular situations, red means maximum, so this is the area, of course, we want to cover as best as possible. And if we move towards the blue, of course, this is the opponent, or represents the opponent goal, and those areas, in terms of cover, are not important for us. And using the field of views and the height maps and the sets, the constraints that result from the rules, we come up, for instance, to a defensive set piece cover utility map that looks like what you see in here. So basically the red circles represent the opponents in this particular case. You can see, so the ball belongs to an opponent. This circle is the 3-meter circle that we cannot enter into before the ball is in play. And then there are the areas which are covered by the opponents, and the red areas are the preferential positioning for our robots, so they can cover the passes from the robot that is going to start the game. Since the opponent team is only using one robot for making the start or restart of the game, there is only 3 remaining robots on the field, which means that one of our robots is not actually attached to this utility map, which is this number 2. In this situation, number 2 is acting as a defensive robot, and its position is defined by the Delaunay triangulation basis that we have on the back. So it's the fallback in this particular situation. So if the ball is there, the goal will be somewhere here, and it will try to cover this area and not cover a pass in that sense. Moving into offensive set pieces, so it's just the opposite situation that we just demonstrated. The main objective is to get into a good position to receive the ball, because before scoring a goal we have to make a pass at least. So normally what most of the teams, if they have the chance to do it, maybe Tech United don't do that because they like to try their passes, of course, and it's nice to see. But most of the teams will try to make a pass, if possible, try to score there immediately. So set pieces in this case are set with a graphical tool that is implement an SBSP algorithm that I just told before. With this algorithm, the field is divided into 10 separate zones, and for each zone we define a set of positions for the replacer. The replacer is the name we give, it's a role, the name we give to the robot that is going to kick the ball, and the receivers, which are the other 3 robots that are on the field. The position of the receiver can be absolute or relative to the ball. This is embedded in the tool. And for the receivers, the need for a clear line between its position and the ball can also be defined. So I can define if I want to have a clear line or not. And the receivers can also be forced to be aligned with the goal. And this is a simple image, just a screenshot of the tool. So the area we are using in this case is this one. And the ball is there. This is our replacer, and these are the positions that we are placing our robots. This is the goalie, of course, so we are attacking in this direction. And for instance, for this robot in particular, we determined that we want to have a line clear for passing if possible, let's say. Again, this has the same problem as the Delaunay triangulation tool. So we can define this, but this does not take into consideration the opponents. So it's really nice so that you can define, okay, if the ball is on this area of the field, we are going to position our robots in this distribution. If it's positioned on the center of the field, we are going to use a different distribution. Those 2 robots need a line clear, that one may not, so it depending. So we can set all that, but still it does not look into the opponents. So we have to bring that into the equation, and we do that by using the utility maps. So basically the rule of thumb is when a receiver has no clear line of sight, and this is something else, and is on the opponent side of the field, because we cannot score a goal directly from our own side of the field, an alternative position is selected based on the average criteria of these aspects. So the robot is positioned according to this tool, for instance, this position, but if there is no clear line of sight, then he evaluates another possible position based on the distance between pass line and closest obstacle, distance to the ball, distance to the opponent goal, rotation angle from a shooter on target, and distance from the predefined position defined by that tool. This, as it's not a simple average, is weighted, and then we have come out with a possible alternative position. On top of that, we have constraints that must also be imposed by the rules of MSL, such as the minimum of 2-meter distance to receive the ball. Otherwise, it's not considered to be a pass, of course, in this set pieces situation, or you cannot enter the 2-meter radius. And not entering also in the goal areas, of course, because this is an illegal attack or illegal defense, depending on the situation. And it is the combination of this criteria and the utility and the constraints that you add up that results in the utility map for each receiver and for the replacer. Okay. So another thing which may be interesting to bring up is that each receiver is also assigned a priority level. So it means that before restarting the game, one of the robots has the highest priority to be the receiver. All of them are receivers, but one is the highest. And then they are ordered by priority. This priority is defined by a leader. The leader may be the coach, the base station, or maybe any of the other robots on the field. And this leader is dynamically elected among the base station, the active robots on the field. This solution is interesting because if there is a fail for some reason of the leader, even being the coach, then we can still do a new election in real time and keep a leader working on. Of course, if the full base station fails, there's nothing to do. The robots will stop. But there is that can be a problem with the coach, because the coach is actually the agent. If the problem with the coach, then we can elect another leader to take that into consideration. So in the following slide, you will see that Robot 2 has used its utility map to define an alternative position for reception, and why, while the replacer has also decided to take the pass to that target. And the idea is that robot number 2 will move to the alternative position only after the start sign is given. Actually, it's not only after the start, but when the replacer informs that he's ready to make the pass. So this is the utility map. You can see that robot number 2 is here. Robot number 4 is the replacer, so he's going to take the ball and try to make a pass. He's already decided that he's going to make the pass to this red area, so this is the alternative position. And whenever he has the ball engaged and ready to make the pass, robot number 2 will move into this position to try to receive the ball and overcome the fact that he's covered by this opponent, yellow opponent on that spot. Robot number 3 is P2. If this fails for some reason, then it still has time to select number 2, which is a 2-meter distance, and make the pass there. And number 3 is the one that is close to the area in this particular situation. And finally, for the free play, which is probably the most difficult situation, we have to consider on one side the striker objective. The striker is the robot in free play that has the ball and has to dribble the ball and make the passes. And the supporter objective. Supporter are the robot or robots that are expecting to receive a pass in the case of need. So the striker wants to get in a good position to kick towards the goal if it is in conditions to score a goal, if a pass has already been done, or to make a pass to a teammate. The supporter has the objective of getting a good position to receive the ball from a pass. Basically, as that. Rules state that a valid goal is awarded only if a pass between two robots occurs before the goal, after the team has regained the possession of the ball, and also that the striker dribbling is limited to a 3-meter radius. Is still 3 meter, or now is we have reduced that? Actually, I don't recall. If not, we will reduce for next year. Yeah, probably next year only 2 meters, right? We don't know. Okay. So to build these utility maps, we start again with the DT formation, apply some rules, and you can see here a static actual gaming situation. And just parenthesis here, these utility maps are recalculated every frame. We are working at 50 frames per second. But we are averaging over 5 frames, basically, a sliding window, so that we can filter out some noise also. So this looks a lot very static, but in fact is being always recalculated. And what you can see here is this is the striker, in this case, is in position of the ball, and this robot number 3 is one of the supporters. And you can see here that, for instance, the 3-meter rule applies clearly here. So this can dribble within the yellow area or red area, but not further away from that. There are 2 opponents in this situation, another here, another in that particular situation there. And it also shows some of the extra criteria we apply here. For instance, even if the robot was closest to the area, we won't go very close to the corners, because if there's a chance to shoot him by a very small angle is very difficult to actually. Sometimes you can get a goal from there, but it's normally it's not a good approach. And then the priority depends on the current conditions. First, if kick from the striker is allowed, then there is a higher priority on this left side, closer to the sideline than to the central or the center of the field, just because statistically we have come to the conclusion that shooting at the goal from a certain angle is normally better, or we get a higher rate of scoring than shooting directly from the front of the goal. So in this situation, you will try to dribble to some position around this red area, and if there's a chance of a line of sight to the goal, then you'll try to kick. If a pass is required, then the higher priority will drive the striker to get an open line to pass to the supporter. So try to avoid to allow these two opponents to get in contact with the ball. Normally you'll turn around, as you know, this is quite common, and try to find a position where the striker has a straight line to pass. For instance, in a situation like this, because of this opponent, the striker will not try to make a direct pass, because the possibility of an active interception is very high in this particular situation. So this blue area means that the ball should not cross in that position, because an active interception from the opponent is very likely to occur. Okay? So this is exactly the same situation, but now from the supporter point of view. So the striker is there, the supporter is not supposed to enter an area closer to a certain distance, and this reddish area is where the supporter will try to position itself in order to receive a pass, or he can try to move close to the area. Of course, then these defenders will try to block it also. But these utility maps basically define the strategy in order to position, and since this is updated every cycle, it will try to move into some open space where he can actually get a pass, an effective pass, and maybe a possibility of shooting at the goal. And then it depends. If the Tech United goal is there, the possibility of scoring is close to 0. If other goalies are there, then the probability is a little bit higher, but okay.
You plot basically the chance of receiving the ball, but you don't plot after that.
Yep.
How big the chance is that it can actually reach the goal? Do you?
Reach the goal in what sense?
If you want to make a goal after.
Yeah, of course. So it, yeah, which means that, of course, in this particular plot, I would say that the chance of getting a pass will be higher on this area, and this area may be still covered by this. But this is dynamic. It's what we have to think about, okay? So it can happen that if I move into it and there is a pass, maybe during that time, this robot may actually move into a different position. So it depends. So in the end, you may have ending up having to make 2 or 3 passes before you actually have a chance of shooting at the goal. Our best goals against Tech United was actually making passes inside the area and having the chance of getting the ball inside the area, and then, because then it's too close and it's much easier to score.
What I was primarily referring to is that the defender just near the spots from
this one? No, the defenders, yeah. These two are covering the striker, right?
The one in the middle.
This one.
Yeah, it looks like if number 3 would move over there, it would be encouraged to move there. But if it would move there, it would be blocked by that defender.
Of course. But if it moves here and there is a pass, even a valid pass, this one will be here in half a second. Okay? That's important because we are looking at static images, but everything is dynamic. So what happens is, by the time this one will get the ball, it will be definitely covered by an opponent. So don't look that in that static perspective. This one won't stay here forever, definitely.
I was thinking want is to move in that direction, because then you even make the situation worse.
Why?
Well, because then he's right
First,
next to it, so
okay,
you cannot
okay.
say,
Let me try to bring some extra aspects into discussion. First, we are only looking at one supporter. We can have more than one. Okay. Second is the fact that you are able to receive the ball even without the possibility of shooting may allow the other one to get free of this tool and move into another position, which is better to get the ball again. So then you'll make another pass. So there's no simple way of explaining that without showing what actually happens during the game. So it's just to get a rough idea how these utility maps, which are updated 50 frames per second, actually works in order to attract or push back each of the elements that are in play. Okay. Also, I don't know how I'm in terms of time. I'm completely lost at this point with the questions. I'm over time, I guess. Yeah. Just a little. Okay. This I will talk this very briefly. And first of all, let me thank Matthijs for his contribution in this part of work. We have already evolved the tool, and this is part also of team coordination strategy, which is the tool for rehearsed set plays. And this tool actually allows us to define a series of moving and passes. Here, this is a linear, very linear and simple example. We can actually create trees that can at some point converge to the same point. And this is 4 situations. We use these 4 situations commonly to make a demonstration in our field for students, for instance. And basically, we define a sequence of actions. In this case, this robot has the ball, and this black line means that he has to make a pass to this robot. What you see here, it can be, the radius of this circle can be defined, and this one means that it does not mean that the robot is actually there. It can be in any place, not outside of the field, of course, within this, with this radius, and this one also can be there or here. So there is a pass in this situation. The next move will be to, and the yellow dot means a movement without a ball. This robot will move to this smaller circle, and this will try to make a pass into this position. Once this one has getting the ball, it will move into that position, this one move into that position, so there's no pass in this phase 3, and the phase 4 is again making a pass from this point to that point, going to the first one. So it is a very simple situation that can be easily demonstrated on the field. Of course, there are again no opponents in this particular situation, but this can be, and we are working a lot on this. There's a lot of work to do still on this kind of tool. And this can be a very powerful tool for if we can understand and maybe learn how strategically other teams work or play, we can use this kind of tool to preset a set of rehearsed set plays that can involve several movements and passes before actually kicking. And this is just, for instance, on our base station, the image of the ball that has already been kicked. The ball is here. This is the velocity vector. Here, this is the receiver. So this is step 0 on setting this tool. So my thanks to Matthijs, because he has done a lot of work on this tool, and we have been involving in that towards something that can actually be very useful. And just to end up, something that has to do with the future, which we call large dataset logging, and actually we already gave a name to this, which is Camelog. And it's somehow similar to what Falcon has described, except that we are not logging, if I understood correctly, of the series of functions that come to a certain action. So basically what we are logging is either all the data that we have in every robot RTDB, even the one that is not shared, or some pre-selected set of data on each robot. And this will be done using large circular buffers for maybe 1 or 2 hours, using a distributed file set, and will be running on all agents, so on robots and on the coach. The objective, of course, is in our case, is to gather all possible pieces of data in an offline state, in this case, by downloading every agent cam log files to the server after a game, for instance. There's a problem, of course, we have to tackle, that is time synchronization of the information about the agents. We are doing this in different agents that are running in different computers. And then we have to synchronize this, register synchronized data in large databases, and then run post-process algorithms on the data. The approach for synchronization, the first one, of course, was, okay, we'll move into something like NTP or Crony. We'll use a base station as NTP server, for instance. The problem is, in Wi-Fi, this can be tricky. It can fail sometime. And then this brought us to do some brainstorming, and we maybe leave this approach and move into this one. So apart from all the information in the RTDB, we are going to create, let's say, or record a time-stamped game status evolution on every agent, and then post-synchronize data among them. How do we do this? Basically, we classify each of the possible actions: stop, drop ball, free kick, corner kick, and so on. And also on the top is start. And all robots will, every time they receive one command, they timestamp this command and add it to this timeline, to this function. This is a discrete function, of course. Of course, there will be, because of using Wi-Fi, there will be sometimes some jitter. There will be some packet loss, for instance. But at the end of the game, this will be such large time function that we can basically correlate, use one as the reference, and then do a cross correlation between these functions, and the maximum correlation factor will give us the best alignment of all the files. And we expect that this solution will actually work and will be a very nice and neat solution for this. For future work, develop new tools for analysis of gathered data, of this data, e.g. of course for debug purposes, this is the first one. Game analysis, strategy outcome analysis, for instance. After a game, we define the strategy, how does it come, and maybe, why not, maybe use it as a database for learning tools for global team strategy, efficiency role changing, dynamic tactics, and so forth. Okay, some references for those that want to look into them. Thank you so much, and sorry for the time I took.
Always have questions. Now, I was wondering, listening to your story, how important is the coach actually still in your gameplay?
I would say that the coach at this moment is much less important than it should be. What I mean by this is that probably using these data sets that you are now going to, with Camelot, that we're going to start to get, we may be bringing to the coach new responsibilities in terms of dynamically changing the strategy during a game, for instance. Okay, based in some sort or learning or other kind of strategic approach. But in fact, for the moment, the coach will basically be the leader. This normally will be the leader. So it defines not the roles, but the priorities within a role, for instance, for a robot. And, sorry? Yeah, and in terms of strategy, it can also change the strategy between some base strategies that depends on game status, game result, and things like that. Yeah, in fact, this leader election we have is a way to move into that direction.
But of course, if you get away with the coach, you get a lot more of these type of negotiations and communications.
Yeah, and we are limited in terms of bandwidth also, right? So, but if we think in abstract terms, the coach is just an agent, like any other robot. So if you think in terms of agents, you have the robots and the coach. So the coach is just another agent, right? So if the coach is responsible for also defining some specific strategy, since we are using multicast, we can use any of the other robots to do the same task. The only problem is the overload that the other robots already have on their computers, since there are a lot of things going down, while the coach is sitting back and relaxing, right? He's doing almost nothing. That's the difference. There's a lot of spare time on the coach that we don't have actually on the robots. Thank you again.
So there's now a 15-minute break. If you want to take a break, there's coffee, tea, and
then the whip came out?
Ja, dat was how much is it? 5 or 6 minutes. You can see the whole food
Now we pull it up with a rope, but we will mount it on the
kleine markers.
machine. Because now you see some areas are double and then it will come
Oh ja. Zie ik hier nou? De glorie.
welke auto is dat?
Ik had wat verdorie.
Van Nederland te promoten.
Maar ik het
Binnenkloppen, dat mocht niet meer.
Je weet niet.
Being confused? But it's too late to come back.
Ja, daar moet er ook nog weg. Nemen wij gewoon die hele zak mee?
Oh ja, jullie kunnen het wel aan. Hoppa.
Het zijn echt dikke borden.
Ja, een mooi bord, hè?
Het zijn niet van die plastic
Kopen dingetjes.
Ja,
Je kunt nog ja, als wij pas om 7 uur bij kan ik niet om 8 uur zeggen. Ja, je moest nou eigenlijk 12 uur lunchen voor als ze dan weer weten dat ik mee gaan. Er lagen gewoon te veel kroketten. Dat is wel allemaal op. En dan altijd fruit tussen, ja, bovenop.
Ik eet die mandarijn
nog. Ik heb nog vergeten om die fruit te doen. Ja, dat is nee, want ze zijn echt gericht. Zij is ook van tegen mij verteld van wat ik één
Ik heb zelf niet zonder handschoen.
Maar ik weet niet of
ik ga verder. Ik zat hier aan het
Oh, dat is de paal.
Hebben jullie wel genoeg peper?
Ja, anders pakken we volgende pas wel.
Hebben jullie ook genoeg peper nodig? Ja? Ja, nee, ja, ik heb nog meer. Maar.
Nee, dus de naam van het dier dat voor oorsprong van mijn vader is opgevallen. Een heel klein beetje. Nee, het is een landen van Nederland.
Ja, basically is het hoofdstok wordt een
daarvoor iets op een
Zo'n klein beetje.
Ja, dat is wel zo.
Dat schema dat hebben we meer gemaakt op basis van dan zorgen we dat we een beetje doorgaan. Ja, in principe. Het zal.
It's just an excuse.
First time? The security guard let me in? I will go at 9.
On the other hand, you can roll in front of
I remember Tuesdays it was like eat a lot of guys and
as I said in Spain, a little bit different. Not the dinner. By 10:30 in the day,
extra presentaties. En dat voor discussiesessies.
is the rest
Yeah, but I can only carry lightweight.
You don't have a question.
I will voorkomen maar. Ja, die is nog niet naar buiten. Je kunt beter dadelijk zeggen, maar we doen die pauze wel. Je gaat die presentatie echt niet op.
Dat beter dan pauze.
Verder in dezelfde PDT.
Een pauze maken?
Sluit op elkaar.
Niet alleen maar volgende deel onze software.
Niet meer leuk zeggen. Zeker, zeker, zeker. Kunnen we verder denken? Wat ik moet doen? Gewoon laat. Ja, maar dat maakt niet wel uit. Ja. Ja, een kwartier hebben we gehad, goed. Zijn jullie het ook? Of ben ik mij gaat daar iets niet in. Dat is gewoon een round bij, je kan dat nog wel bij. En dan naar links kuren en dan
Oh nee, daar misschien.
Jawel, er zitten van die dingen. That's to you.
Sûrement mieux. Ça. Hop, voilà, parfait. C'est bon.
Okay, so I will present you some of the relatively small advance of our team compared to other teams. That some advance for our first year in MSL. So first, I want again to thank all the team for their support. And especially Kambada, especially Tech United, especially Falcons, because their support is very important for us to be able to play a game. We expect to play a game this year, maybe in Portugal or maybe even in Bordeaux, but it's still a difficult challenge for us because maybe we'll talk about that tomorrow. But starting in MSL, it's you have to face an amazing quantity of challenges. So I won't tell you anything about machine learning because to make machine learning you need to get a team of robots, and we are still trying to finish our team of robots, and actually we have made some tries for machine learning, because we have some people, I show them a video using YOLO and for just robot recognition and ball recognition, and it's working very well. But last year it was difficult to use because of embedded architecture. Next year it will be okay with what I will present. So. What are new features? Actually, since Sydney, everything is new because we started from a blank sheet again with the experience of the first year. So we are trying to make an improved coil gun. Why do we have chosen to make an improved coil gun? It's very simple. Is that we will not get the same gameplay as the top team have. So we try another weapon, just shooting very strong. It can be another idea. Then we try to make a new propulsion structure to have a reliable embedded processing architecture with reliable sensors, and also a new ball handling system. So everything is new. First, I was asked to explain what is our new coil gun system. There, I will introduce a multi-coil clicking system to put a little bit on what hypothesis we are working. We decided not to change. We keep the same weight of copper. We keep the same overall capacitance of capacitor to compare between one coil gun and 4 coil gun. But instead of having one big coil, we divide it into 4 identical smaller coils. So for the solution with 4 coils, we use 4 1200 microfarad capacitor instead of one 700 capacitor. This is the structure. Here you have the 1 coil structure. Here you have the 4 coil structure. And there is also an iron shielding, and there is iron here, and here. It's very important. First, we have made a model under MATLAB Simulink for modelizing the 4 coils here, and the mechanical part which is here. This is the submodel of the mechanical parts and the submodel of the coil gun. And in this mechanical part, there are some lookup tables because we get the inductor value and the force value here, depending on the different currents, I1, I2, I3, I4, and the position of the plunger on the coil gun. And for that, we have made some modeling using FEMM, which is a finite element tools for electromagnetic simulation. With all that, we got some interesting results, I think. First, we have to focus on what is the energy in the capacitor. What is the energy stored in the capacitor? I think it's important because, as we can see, you can store 450 joules in the capacitor. If we take this kind of kicking system with plunger, an iron rod, an aluminium rod on the ball, if we put all the mass reported to the ball point here, it's equivalent to a ball of 0.7 kilograms approximately. And if the total energy of the capacitor was converted in mechanical energy, the ball speed would be 36 meters per second. That means 126 kilometers per hour. Yeah, but I think it's very important to see that, because that means with the simulated output or with the real output, now we have solved our problems on the kicking system. We get 11 meters per second about. That means you have kinetic energy of 42 joules and energy conversion of 8%. Yeah, that's incredibly low. So what we have done is to put four coils instead of one, and with the 4 coils we can reach 17 meters per second. It's not really exceptional because kinetic energy is only 100 joules, but energy transfer is only 22%. That means there are still 78% of loss, but there are 2.3 times more power transmitting that with the unique coil solution. So that's quite interesting finally. Here are some simulations with the hypothesis I have given. You can see that with one coil there is a force not constant but continuous, and going to about 70 kilos. Whereas using 4 coils, you have 4 coils. Of course, the 4 coils are triggered individually. First one, then when the bar advances, go further, the second one, on the third one, on the fourth one. And in an optimal situation, it had been optimally tuned by hand. With an optimal situation, you can see that we go to an instant force going up to 140 kilos, which is much more because the coils are smaller, have less turns. So we get higher currents and higher instant force. It's like what we can see in SSL. In SSL, currents go up to 400 amperes. It's much more than us. And for the ball speed was reaching about 11 meters, and here we reach about 17 meters per second. Yeah. So for the result, I say it improves the energy transfer by a factor 2.4, and there is still to improve. We have a kicking PCB system which is operational. I brought one here, if you want. It's after a few explosions, it's operational now. And again, this one has been corrected. It's not the last version, but yeah, this is just heatsink. For that one, I thank again Tech United team because we used your design to make our own one, but since the first version we have made several modifications now, and we have replaced the IGBT by a MOS, for example. It's faster and less expensive. Okay. This is all for the multi-coil kicking system. Again, we have made another evolution for the omnidirectional mirror. In Sydney, I presented an omnidirectional mirror built in a way that the image of the field was not distorted. This is interesting, but there was a very interesting answer, which was, okay, but near the center, there is less definition, and it's important to have definition in the center. So we have decided to make a new one, which is a strange mirror. It's an omnidirectional mirror made of two parts. The first one is the one I presented in Sydney, and the second one is a second one like the one presented in Sydney, but at a different scale, so that here in the central part you can see a very wide field of view with, as you can see, the field is almost not distorted. It's a simulation under SolidWorks. But on the real one it's again almost the same. And around here you can see this crown is a view very close to the center of the robot. So you have in one camera a view which is synchronized between the overall field and a view just around the robot for 1 meter about. So about 1 meter. Yeah, you can see the ball. On this one it's a little bit less, but we have a version of 1 meter. And this can be adjusted also because it's the mirror designed by finite elements, so that's not difficult. Further new things, we have introduced a different robot configuration. I'm not a historian of the RoboCup, so I don't know if this configuration was tested or not. But we have decided to make a test with 4 omni-wheels pentagonal structure. That means, as you can see here on the new base, we have 4 wheels here, and there is one missing, which is the rear of the robot. The front of the robot, sorry. This is interesting because here we have an opening angle which is very wide. There is a very good stability and an opening angle of 144 degrees, which is very interesting for the ball handling system, as we can see later, as you can see here, for example. And there is, of course, a problem with the hyperstatism of the 4-wheel system, and we try to solve it. This is our conception of each motor block, and each motor block is put on 2. I don't know the name. It's like 2 ball bearings. 2 ball bearings on this side, and on that side there is a rubber, there is a soft rubber contact, which can reduce, if there is a misalignment of 1, 2, 3, 4 millimeter, it's okay, it will be compensated by that. So it seems to be operational, and it seems to be reliable also. Again, our ball handling system was not good, so we tried another ball handling system. For now, we are not precise enough. So we said we will try to make a ball handling system which is tolerant to a wrong position of the robot of 10 centimeters, 15 centimeters, something like this. It's easier for us in the first step. So starting from that, we decided to take advantage of the large opening scale of the opening angle of the pentagonal base structure in order to put many omnidirectional wheels. There is a mistake on the conception. It's based on water system. It's almost the same configuration for the two central wheels. And after we have added other wheels. And more than that, we have added here some balls also. So that the ball can slide on the front of the robot very, very smoothly. That's interesting because if the ball reaches the front of the robot, it will be sliding on the ball, and the trajectory will not be stopped with the risk of rebound, but it will be moving to the center and stopping smoothly. So it reduces the problem of rebound if the ball is strike a little bit too strong. I will show you some videos in a few weeks, in a few days, because it's mounted for just a few days now. But the first test seems to be very, very interesting. Next step. This is just an evolution for us. In Sydney, we were a little bit annoyed by USB troubles. We get many troubles with USB. So I said that we will get rid of USB. That's done. We have replaced our small computer by a good one. Yeah. Yeah, it's the latest i7 computer with 6 gigabytes of RAM and GTX 1060. And there are 4 PoE ports and 4 serial ports and everything we need for 5 years. And it can be also powered directly from the battery. There is no need of a power regulator first. So it's important, it's much easier for us. So it solves all the problem of cables in the robot, of course. There is no cables now. And it gives us some power to make some experiments for example, on learning in the near future. Because maybe we will try to make some opponent detection on using camera and as I said in introduction with YOLO, using deep learning. And also we will use our lidars. They are installed there for collision avoidance. And we are studying the possibility of using a very interesting lidar. Which is 50 Hertz and 0.014 degrees of resolution. That means 2.5 millimeters at 10 meters of resolution. Well, still there is a little problem, which is the price, but we are discussing. Yeah, it's about 12,000 euros, something like that. Yeah. But it's 360 degrees, so you need only one by robots, not two. Because at this time we have two lidars, and they are quite expensive also. Actually, I think we need a Black Friday. Yeah, that's all for us. Thank you for your attention. If you have any questions.
Yep. Which has to do with something you just propose yourself to do, which is to deliver some videos on that damping / involving of your ball grabber solution.
Yeah, sure.
Yeah. So
Can we expect to have that?
Yeah. We will get it. We have still one iron rod missing because it's a little bit complex to assemble. Because of the part which is not I don't know the name in English, but there is a part which is not into the bearing but outside the bearing, and this one we cannot assemble and test it fully at this time. But I think in 2 weeks it will be okay, and we will post. We make some post of improvement on our Instagram account usually. Yeah.
That the battery still lasts for.
Yes. Yeah. We address this question first. It's the only thing we have kept from our last robot is the battery system. We are using Makita batteries from Power On Tools, and it's 5 ampere hour. So the PC power consumption is about 11 amperes on 12 volts, so it will last on one battery 40 minutes, something like this. It's enough for one game, and we can change at half-time. It's possible.
How many batteries of those do you use?
Oh, we put only one battery for the motors and one battery for electronics. Yeah, 2 batteries. But battery for the motor, you can play 3 weeks. That's no problem.
3 weeks.
Yeah, Maxon motor.
Are you considering the kicker too?
No, but no, we are playing 3 weeks at this time. Okay, Tech United can play 10 minutes.
The laser range finder, is that a 2 or a 3D one?
No, it's a 2D.
So we had one once on our platform. We decided to kick it off because of power usage, heat generation, and limited use, and especially the last one. Where do you need it for?
Actually, maybe it's not necessary. Maybe really, maybe it's not necessary. But we still don't have your background. So we wanted to. When we studied, to be honest, when we studied the video we have taken during the RoboCup last year, we have seen on the video we have made on the base station. We were talking about that during the lunch. We have seen that, for example, Tech United sees the opponents on a reliable way at about 5 meters, something after it's moving very fast. We have seen also that water see the opponents at 2.5 meters or 3 meters, but not more. And the best one is Falcons. They can see opponents at 8 to 10 meters, something like this. And so we said, okay, other teams have a strong background with cameras, and they can see opponents up to 5, 4, 6 meters, but finally, it's not so much. With a LiDAR, we have some experiments with it. There is no problem at all to see the opponent at 10 meters. It's reliable. So we said that it's a good way to add some information to the camera and after to match the information. It's another channel for getting information about the positioning of all the robots on the field. Of course, it's not cheap, but yeah. Yeah.
So, and we are very actively sharing all the local world models of the players, such that, let's say, with the 40 hertz update rate, we have a more or less global view of the whole field.
Yeah. I know that's no problem for.
Okay, but if you have the laser scan, what you get is a series of points, but the points are meaningless. So you can make all kinds of assumptions about the meaning of those points. But if you would have segmentic, let's say semantic segmentation of your images using tools like YOLO, it would be much easier to get meaningful detections.
Perhaps then using the range finder that gives you a 2D set of points to the nearest object.
Actually, with the lidars, we are detecting blobs. And blobs correspond to objects, and at the age of detection, there are only robots on the field. So we can know that all the blobs we are able to see are robots. And after, of course, you get the camera detection. You get many information by camera, but we thought that getting also information with the lidars was a way to add strength to the overall detection of the whole field. And to be honest, we get the 12 lidars for free also.
Yeah, I understand the principle.
Yeah.
I think it's an expensive approach.
Yeah,
but for instance, consider that Falcon accepted a challenge by Rene to bring the cameras down. Then depending on the height of your lidar, you may not see any opponents at all.
No. That's true. That's true. But that's why there is a scale here, and we can move the lidars at the height we want.
Yeah, because
of course.
My question was that do you intend to place the lidars at different heights
yes.
to avoid interference?
Yes, there is two reasons for that. First one is that it can be interesting to identify opponents from robots if there is a big difference of size. For example, if you play against water, they have big robots, so you can distinguish between their robots and your robots. This is the point. And the second point is a technical point for lidars. There is you should avoid to put them on the same plane because there can be some very strange comportment. Even if with the lidars we are using, we are using SICK lidars and they are reliable. Yeah.
Did you look to the automotive solutions? They have also using lidars. They
yes.
also have the problem that are the same height and not all car is different.
Yeah. This is a PC for cars or for cars on bus.
But I mean, they have the same problem that they have interference of their own.
No.
So if you are at the traffic jam up at the traffic lights, and there will be a few of these cars to the traffic light, they all
Yes, that's true. But actually, that's true. But I think the lidars manufacturer are focusing on this point at this time. And the experiment we have done with the lidars shows that sometimes there is one point missing, one point which is wrong. But after it can be easily solved by post-processing. So it's not a so important problem, I think.
If I look at the pentagonal structure of your wheel configuration, what does that configuration mean in terms of velocity and acceleration you can achieve?
Maybe why do we choose four-wheel configuration? Basically, we wanted to make lightweight robots, and we said we started from a feelings during the RoboCup, which oriented our choice. We went to see the SSL match. On SSL games, robots are very fast. Very, very fast. Consider at a scale factor from MSL, they are 5 times faster, something like this. But they are lightweight also. And we say, okay, if we want to do that in MSL, maybe not for us this year, but in 2 or 3 years. It's impossible because there is a problem. It's possible, but you have to have a very, very low gravity center. If the gravity center is a little bit too high, when you accelerate, the weight is put on the rear wheel, but the rear wheel is perpendicular to the torque, and so you don't have any torque on the rear wheel. So it's impossible to have very strong acceleration with a free-wheel platform which would be lightweight. Starting from that, we said, okay, we need to get some torque on the rear wheels in any situation. So this is not perfect, of course. It would have been, this configuration would have been perfect. But after, it's difficult to turn. So, or to have the third wheel in front. Having the third wheel in front is a good solution, but it's a problem with the ball handling system. After, on for the kicking system also. This is why we study the different configuration, and we say 3 is not good. 4 is the configuration used by SSL. So we said okay for 4. But we want to have a Jacobian matrix which is almost the same in going in all the directions. So we will try to get the most regular structure as possible. And so we said, okay, we have to free the front part of the robot. So let's try a 5 wheels robot with 1 wheel removed. Yeah, that's approximately the thinking we had to choose this structure. The first tests are very interesting. Really, it's much smoother than the free-wheel platform, and there is no vibration. The vibration you can encounter with the free-wheel platform, you don't have it with the four-wheel platform. It's like moving a Formula 1. It's very, very smooth. We will make some videos also as soon as possible. Maybe it's not a good solution. If it's not a good solution, we will have a third generation of robots. That's still possible.
Thank you very much.
Dat heb ik even geprobeerd. Oh, zo ja. Ja, oké. Goed. Oké. My name is Dirk Punter, and I'm presenting you the state of the art of the RIF team. RIF stands for a riff, a guitar riff. That was one of the founders of the team played the guitar, or he was at least interested in playing guitar, so he thought that would be a nice name for the team. RIF can stand for resistance is futile. Something to mention. You can also couple it to my institute, Fontes, then it's Robot Initiative Fontes. Yeah. We do this from Fontes ICT. It's one of the Fontes institutes. I heard that my colleagues from Mechatronics are also here. So we take a software perspective on the RoboCup. And this is also what I can tell you. You won't tell any details about torque or any mechanical things. I will try to tell you from a software perspective. Rick Pijnenburg is with me. Rick, you are already on the photos. This is our team. The upcoming 2 days, also Matthijs Frenke and Adrien Guillot, and probably Milan Havelach will also be presenting, will be present here in the workshop. This is our team. It's actually the result from a lot of student teams we had in the past. So RIF can be explained, our progress at least, in a way like this. We have progress and we have time. And this was usually the way of working we had with student groups. We worked 20 weeks and then we had a brainwave, or brain dump, I would say. So starting 2018, we started with a development team of students and lecturers, and start from a perspective, okay, we need really a developed team over semesters for a longer time. At least we were a little bit above this level. But then again, this went down. And I think this is also related to our hardware. Our hardware, we are using the Turtle 5K hardware, and we lease those machines. But after a lot of time, some things break down, and we had a lot of problems to repair this. So our statement that we have a software engineering approach and having working hardware was not valid anymore. So we were inventive, and summer 2018 we decided to go for a riff-raff, a mixture of technologies based on skateboard technology. And basically this was born by the idea that some of the students were bringing in their skateboard, and those are actually very cheap motors, but there's also fast motors. And going for a new hardware and having also a hardware opportunities to buy it at AliExpress made us to go for this hardware configuration. We made a lot of designs on this, and we also had a review by the VDL Robot Sports on this, and this gave us confidence to continue with this. So actually we are developing at the moment this platform. Basically this is 3 skateboard motors, 3 FESCs and an ASP 32. This is the bottom of our hardware. We use batteries, just AA batteries, and we split the power for the motors and the power for the PC. This is currently developed by 4th semester students, so end of 2nd year students of Fontes ICT. And we have 2 groups working on this platform to make. Going a little bit up in the architecture, in the hardware architecture, we choose to get for a Jetson TX2, TX2, and for an, I think it's a $50 camera, but this is really just a prototype, and we have a lot of experiments done in the last couple of years with a Ricoh camera, with all kind of cameras, what could help us. Currently, this is the status. It's not stated that it will be this camera, but it's at least this technology. Going to the architecture of our software. This is basically a hardware abstraction layer that pushes information via object detection, localization to so-called skills, and this is the action mechanism. Basically, this is the set of components. So we can have two ways. We observe the environment with our senses. This is the perception part. And then we act, and then we move with the motors and kick with the motors. And this is basically think the way you act. It's intuitive. The other way, it is basically also the status of our software, that we try to be intuitive in this way. The second loop is using the world model, and actually we don't have a world model anymore. We had a world model, but we don't use it anymore. And that's basically think before you act, and then you can have more intelligent actions. I will come to that later. Basically, this is also the focus of our work. So we have perception and we have action, and that's also the interest of our research. We do applied research, and having a perception AI that detects objects such as a ball, an opponent, and we have actions to help us with action selection. We use AI because it's non-deterministic, so sensors are noisy, and we hope to deal with AI to improve this. Focusing on perception AI, that's basically the input is a set of sensors that you can see, and then that's distributed along our architecture. An example not related to soccer robot, so also not to the RoboCup MSL, is this way we developed with perception AI. This is a learned neural network. It's open POS of Carnegie Mellon. This is a trained network available also for software engineers to implement it directly. You can use this with a JavaScript and also with a very low budget camera, and it helps you to detect gestures or poses of people. Now this is what we use for what we have developed with students, and it's then an interaction module that can be placed upon an AGV. So the idea is to recognize poses, and that helps to detect poses that can give a command to the robot. And also this robot has the so-called Disney eyes to interact to the environment, what it is intention to do. So this combination, the perception done on the robot and giving intentions back, that's an example of perception AI. Now going back to the RoboCup, this work in progress at the moment. When we want to know where we are, we want to do localization, odometry, and an IMU can be used for positioning. We actually use this odometry at the moment, and we intend to use gyro information, the IMU. But we also want to look at how we can position ourselves better in the field by looking at the field lines. And there we want to use supervised learning and combine the information we get from the supervised learning results with odometry and IMU information. We can combine it, do diffusion, and there we have to get both information that will be better than just having the odometry or the IMU information. That is an example of an experiment we do in the context of our RIF team. Emma Buitendijk, I think some of you were mailed by her to ask some questions. That was basically about the setting that when we want to do this experiment, we also need to know things about ground truth and other things about you. So I guess some of you were mailed by her. Talking about action AI, this is basically, we have a world model, we know where we are, or we know the status in the world, and we need to define the action. You have already given us an in-depth talk on what you do as Cambada on that. So we want to have these utility functions to select from states the right actions. And these actions are then skills like moving, dribbling, passing, shooting. We're working on this, so it's not work done already, it's not finished. But an example, this is at the moment the status, it's not quite up to date, but this is the red we haven't done, but for example the passing and the shooting we are working on. An example of this is using the navigation, and there we use artificial potential fields. So we have a model of attraction and repulsion in our planning principles that we can make a naturally movement along objects in the soccer field. Going back to what also is related to our research, that's basically the thing that we're thinking in models, and usually what we see is that the state machines are the modeling features for the soccer, and also inspired by the people from Falcons, we have researched the behavior trees, and this gives us a little bit more insights, more structure, and also a modular way to develop our software. Because these behavior trees, they have hierarchy, they have pre and post conditions for the actions, the skills we want to take, and this is the way we want to address also the skill development. For the research it's then interesting to compare those things. What we think our next steps will be, apart from this navigation and this dribbling, is to go for further work on ball detection and basic skills. Then go for localization and navigation. What you can also think about is to engineer your own robot behavior, and a next step, very futurist, will be then looking at opponent robot behavior. This is a kind of, can't call it a roadmap, but this is the idea to work more in a more structured way on new skills. Something about the software part. We have invested a lot over the last year in continuous integration. We do that in the GitLab. We have very preliminary actions on that, like linting and building and testing. And our testing efforts evolve in a more structured way, so that we can do the tests on skill level as well as on system level. Simulator, that's also important because when you have no robots or no working robots, then you have to simulate a lot. Right? So the skills so far were developed with these 2D simulators. That's the stage simulator in ROS. We have developed a prototype for a 3D simulator in Gazebo, where we can also use the RTDB as an interface with other teams to put another team into our simulator. This is really the 3D simulator is work in progress, and it has to be matured. This was my presentation. Are there any questions? Yeah.
You attempted using potential field navigation.
Yeah.
As already the example you show,
yeah.
You don't take optimal path. You're already clearly driving into towards the road.
Mm-hmm.
Well, for example, it's more fair to go on the left side around it.
Yeah.
options because yeah, this is something we in the past used.
Yeah.
But we're jumped into this kind of non-optimal decisions, which yeah, result in clustering of robots. Well, yeah, we're not about interested in where the opponent is, we're more interested in where the empty space is.
Yeah, I agree. But this is just an example, but and there can be many more situations on this. Yeah, we are not that far that we can have the complete match and see for other options. So we didn't do the exercise so far. No. No. Yeah, that's a warning. Yeah, I thank you for the warning. Yeah, yeah. Yeah. Yeah.
And then very late you decide I should now actually go right. Then you still have the inertia.
Mm-hmm.
And that will lead to collisions. We had the same issue.
Okay. Yeah.
2 warnings.
2. So you use another way nu.
Yeah.
Okay. And what are you using?
That's actually a paper from Tech United from a long time ago.
Okay.
That's basically you have your initial position, your target position,
Yeah.
and if there's an obstacle in the way, you put a sub-target next to the obstacle.
Okay. Yeah.
So the new target will be next to the obstacle.
Yeah.
And by the time it reaches that, maybe the obstacle is gone, and then you can go to the initial.
Okay. Yeah. Okay. Yeah.
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 But I said, yeah, like I said.
No, but I mean, I was thinking on the year that paper was published.
Okay.
So it was a long time before I think I can find it.
We look at several things here, and this was just to show you that this was developed as one of the skills. Yeah. Okay.
I saw in your presentation the think before you act and act while you think.
Yeah.
Statements. So I think it's looking at our software, we mostly think before we act. Do you have an example of the other way where you act while you are thinking? What kind of actions do you have in mind to implement?
I think that's a philosophical thing, of course. But what we're trying to do to work with these the state to actions mappings, that we can do this second level much more fast, because you are always too late in football. So having a situation and match that to an action, for example, this dribbling would be that kind of actions. Yeah? Okay. Yeah.
I've seen that you are using surface learning for positioning with the camera filter after.
Yeah.
What is the input of the network and what are the outputs?
The inputs are photos. We made a lot of photos of the field, 1,400 photos that are scripted, so they are simplified. That we have no confounding factors in these pictures, and these pictures are actually you can see the field as a grid, in which you take several positions, several angles, 12 angles, I think they are on each position, and those are given as inputs for the machine learning algorithm. And the photos were bewerkt. They had to be in a square. They had to be no yellow surroundings, for example. So they are really green and white pictures, and this is given as an input. Yeah.
Yeah. Just a follow-up of the
Yeah.
question. Of course, you understand that the field is symmetrical.
Yeah.
Right.
Yeah.
So following
Yeah.
You solve the symmetrical issue.
Yeah, that's a good thing. We are not that far on that. Yeah, yeah. So I think the solution will be in a gyro or a combination of input with other sensors. But we are not that far. Yeah, yeah. It's really a work in progress. So currently the student is working on this assignment. Yeah.
Okay, a word of advice from
Yeah, precisely. Yeah.
Never use a campus.
Okay. Yeah.
I'm not joking, because in the type of environment where we play, there's a lot of steel, there's a lot of interference.
Yeah.
So the magnetic
Yeah.
field is never.
That's we also heard that from the other team, so we don't use that. Yeah. Yeah. Okay.
Thank you very much.
Ja? Oké. Nee, hoef jij ook niet te hebben. Hè? Nee.
Okay, we have a little change in schedule. On a suggestion, we place the Tech-Unite team presentation after the second break, so we have a break after each of the teams. So right now we have a break of 50 minutes, and afterwards we will continue with Tech-United and
Ja. Mooi jongen. Ja. Ja, dat moet eigenlijk wel, hè. Op afstand, nu kan je hem heel een beetje bijstaan, maar je kan niet alles volgen, dat is niks. Je moet gewoon op... ja, gewoon... ja, je moet gewoon op AliExpress zo'n gimbal kopen en nog goedkoper. Ja. Weet je waar de SD-kaart stond bij deze camera zit? Weet je waar de SD-kaart stond van deze camera zit? Ja, ja, weet ik wel. Dus volgens mij is dat... Ik vind het eng om een tape eraf te halen, maar... Nou, waarschijnlijk is het echt... Hoezo? Nou, hij zit... we nemen ook op met de camera. Dat we een ding hebben gelijk, een extra beeld. Ja, ik zit kijken, maar het moet toch niet zo moeilijk zijn, hè?
Ik heb een sticky.
Met de presentatie. Kijk, dat is VDL zeker, hè? Of niet?
Ja,
geweldig.
Sports heet dat.
Heb je veel filmpjes zo? Moet je even checken op...
Dus ik zie eigenlijk al
Zet hem even op de windbordje op. Dan is hij iets stabieler op het algemeen. Ja, dat zal maar even kopiëren naar de laptop zelf, want we hebben met de livestream zit een soort screenshare programma zit eigenlijk kapot. Oh, je pakt dat filmpjesbron of niet? Ah, ja, maar ik ook niet.
Nee, ik heb het zeker. Oh. Nee. Wil je hem hebben?
Ja, dat heb ik niet. Deze twee?
Ja.
Ja, nou zeg maar. Wat mag ik op de livestream doen straks? Wil je al RoboSport?
Ja, gewoon via RoboSport.
Oké, ja.
Het sponsor is er niet echt natuurlijk.
Ja, hij is alleen maar volgend. Ja, dat is Vind je dat op? Oké. Vind je dat op? Ja, dat is goed. Die betekent uit. Ja. Doe naar links, dan naar rechts. Naar je rechterhand. Is die los? Dan moet ik even aanmaken. Het zit niet erin, maar... Oh, dat is slim. Deze dan. Nieuw, check je filmpjes. Ja, dit is jammer. Deze voor jou, deze mag jij nog niet klikken. Durf je klikken proberen?
direct tegenkomen. Dus dat je er wel een lijn kunt krijgen, niet te dicht bij de ik weet niet of dat zou dan wel een
Nou, je kunt dus een simulator, als je daar in SJA inlegt, dan zou je volgens mij goed kunnen meten hoeveel botsing je krijgt. Zelfs bij simpele vallen, maar dan moet je zelf proberen. Ja,
ik ben er zelf niet mee bezig.
Dat is een hele mooie test. Gewoon 2 perfecte profielen. Kun je daar met PFM die op race doen, dan kun je daar met PFM ook echt nee, maar dat paper is, er staat op de site van er staat geen jaartal bij. Maar er is geen jaartal. Die hebben wij letterlijk. Dat werkt al jaren. Maar blijf maar vasthouden. Ik heb het nu net zo gepakt. Dat is ook zo bedoeld.
Kunnen we eens kijken of rubberbanding, dat jij losse bedragen dus hebben ze toen ook ik weet niet meer precies hoe dat zal gaan. Ze zijn niet strak mee bezig geweest. Ze zijn wel mensen die dat gedaan hebben. Daar krijgen we legaal wel dus die potentiaalvelden zijn voor mij eigenlijk alleen maar om te bepalen waar willen we naartoe. Welke lijn kunnen we nemen. En daarna de obstacle avoidance. En daarna
Op dit moment wel wat simulaties laten zien. Dat is gelukt. En de code staat online, maar dan niet in de
Wij gedaan hebben. Ja.
Ja, dan ga je graaf rekenen, wat is een shortest path?
Ja, ik pak een shortest path over die graaf en later dan heb ik een bloempad met die tekst op. En ik heb een volgende laag die dan wel de bocht afsnijdt.
Die fine-tune.
Ja. Maar dan weet je al, ik wil linksom en dan denk ik, nou kijk, want dan dan kun je nog meerdere lagen oplossen. Dat is een manier. Dan menen we, dat doen wij, dat kunnen we echt niet zeggen, dat doen we aanregelen, maar. Nou, je hebt de eerste gewoon pad op. Dit zijn stukken van maar 2 meter. Ik zeg van ik wil vandaag punt en dan wil ik daar naartoe zijn en ik wil dit doen. En ik later kan ik doen. Ja, het pad is heel goed. Ik zit op de oriëntatie. Roteren is eigenlijk heel simpel. Je doet dat wel oriëntatie, dat maakt mij niet uit. Als je aan het rijden bent, als je niet met de bal bezig bent, dan wil je toch naar de bal kijken. En ik kan toch om me heen, ik kan niet op de bal bent, ik kan net zo niet op die kant. Ik kan gewoon blijven kijken. Want stel dat die bal in één keer komt,
Nee, dat is ook goed.
Maar dit wordt de mogelijkheid om te passen. Want als je dan een grond vast tot vangen, dan zit je ook niet op te wachten.
Nee, dat is ook een van de dingen waarvan ik ook heb gedacht, dan maakt het veel makkelijker een robot te komen. Persoon moet ik kijken waar ik ben. Ik kan wel blind lopen, maar dan gaat het nooit zo snel als ik kijk.
Nee, maar omdat wij vooruit kunnen rijden, hoe hard ze wil.
Ik vind wel considered
Maar dat is een manier, hè? Maar dan heb je dat soort dingen en dat kun je heel makkelijk gewoon in een simulatie op Ja, maar ja, dus even de andere werk ook. Meteen het werk. Ja, maar als je het afleidt, dan is het hetzelfde probleem. Je moet altijd eerst maar tegenstander afleiden. Dat komt ook niet. Dat kun je iets mee doen. Dan is het de vraag hoe nauwkeurig is die vector niet. Ja, maar als je 20 keer per seconde update, dat is wat wij doen is we pakken de tegenstander, dat is gewoon aan het steunen. 50 centimeter van de 50 centimeter omheen. En dan 4 punten omheen en dan met een cirkeltje allemaal in nummer staan. Anderhalf omheen. Heel punt anderhalf omheen komen. En je mag dan niet van de ene punt wachten op de andere. Dat zijn dan die lijntjes. Maar niet. Het enige waar je dan mee in de komt, dat werkt heel goed, als je band moet zetten. Dubbelslag, maar zeggen, reken eerst waar je toe doet, dan krijg je iets meer met de snelheid van de band meenemen, nog een keer doen. Wij doen het. Dan weet je ook als je meegespelen hebt, dan kun je lijken. Maar dit doe je af en dat kan je daar ook niet gebruiken. Iedere keer hebben wij een setje van belangrijke bollen. De eerste bol dat we gaan naar de bal toe hebben. Die met de bal. Die moet ik rollen. Dan wordt het even aan die andere kant. Eindje af.
Is ook nog waarschijnlijk wat beneden zo. Kluis is vooral de kaars, dat is een dikke boot.
Ik moet wel even zeggen, ik vind jij het heel goed doet. Ja? Hey, ik ben weg. Wees heel fijn al.
Okay, hi everyone. My name is Ense and I'm gonna present to you the team presentation of Tech United. First, a little bit about the content of the presentation. Our goal for this weekend is to share information amongst each other. So for that reason, we sent out a questionnaire asking if you had any suggestions for our presentations and sending you suggestions we had for your presentations. So first, I'm gonna give a little bit of a recap of what happened last year. Then I'm gonna discuss some requested topics. They were shooting with machine learning, dealing with light condition changes, and our path planning. And after we discussed the requested topics, we really have a member that really wanted to share something with you that he has been working on. So the second part of the presentation will be held by Peter, who's gonna tell you something about our future learning behavior of opponent teams. So first a recap of last year. We won first place in RoboCup Sydney, which was a really big deal for us because we finally broke our even year spell. We have only been able to win in even years so far, but 2019 was a game changer for us. The past 12 years we've always stood in the final 12 times so far. And on the Portuguese Open we became second place. First place went to Cambada, so congratulations. So a little bit about our team. We're a team from the University of Technology, where you are right now. We're a combination of people that do work for our team as a hobby and people that work for their education in our team. Hobbyists, we currently have about 22. We're a mix between bachelor, master, PhD, TUI and alumni. And the biggest part right now is master students, which is 36%. And next to that, we have a couple of projects that people do for study points. Over the past 2 semesters, we've had 5 bachelor students, 1 PDN and 1 master student. So one of the projects that is currently done by one of our bachelor students is shooting with machine learning. It has been a project that we've been working on for a long time, and right now a bachelor student is looking to implement this, and we're expecting results within a few months. So what is the basic idea? We have a duty cycle and a lever height that we put into our robot to gain a velocity and an angle of output for our ball. Let's name them K and L. We made an inverse model of our robot and ball and shooting mechanism, so we can estimate if we have a certain velocity and a certain angle that is desired, what our duty cycle and lever height should be. To improve that, we actually measure the output that we get from our model using our Kinect V2 camera, which is an Xbox Kinect camera. And by tracking the trajectory of the ball, we measure what our actual velocity and actual angle was. Well, using an extended Kalman filter, we can trace back what the components of our inverse model map should be. That way we use machine learning to improve our model for shooting. The bachelor student is currently working on implementing this, so keep track of our Twitter page, because in a few months we expect results from this, and then we can let you know whether it was a worthwhile effort and how much it did improve. The second question was regarding dealing with light-changing conditions. We currently use color to track the different parts of our game. So we use the yellow color of the ball to see what the ball is. We use the green of the field to see where the field is, the white of the lines, and the black of the obstacles. We use the color of the green to determine we use the color of the fields to determine to adapt to the light changes by calibrating the yellow ball beforehand. So what will we do in the future is this. We'll use machine learning algorithm to detect a convolutionary machine learning algorithm to make a feature map of the different components in the field. That way we can use that to see possible locations of the ball. For each possible location of the ball, we use neural networks to see if what the probability is that there is an actual ball there. Well, doing this has a couple of advantages. For example, we're not dependent anymore on the color of the ball to see the ball. We could use another color ball, we could use a ball with multiple colors, and that way we're a lot more adaptable to changes in the environment. Well, this is what it actually looks like. You can see here how we detect the lines. You see the black lines, we see the difference between the green, then the white, and the green. And that transition is how we see what the lines are of the field. You can see here a little animation of the reconstructed image. That is for us humans, not for the robots. The robots can deal very well with a round image of the field, but this way we humans can also see that is a correct image of the field. The last question was on path planning. We're currently revising the path planning For a large part, mostly because there's a couple of components that we do not like and would like to be able to adjust in our path planning. An example would be that we cannot currently give an end speed to the location of the robots that we plan as a target. That way we're currently planning this year to start revising a large piece of the path planning. So for the question regarding that, we'll keep you updated, and hopefully RoboCup 2020 will give you a bit of the status on how much we've improved that. And then now I'll give the word to Peter on the learning behavior of opponent teams.
So, and now for something completely different. I am one of those hobbyists that we talked about before, and I'm now into my 10th year of being a pensioner.
Just a second, from the presentation.
Welke knop moet ik hebben? Deze? Zo, okay. I've been doing AI for a long time. I started doing that in 1968, in the time that we were building expert systems. And I wanted to do something with AI in this team. But after thinking about it and doing all kinds of stuff, I decided that learning how to play soccer was too difficult. So instead, what I wanted to do is to learn how our opponents behave. And we have a lot of information, log files, where we have a lot of details about what our robots are doing. And I want to use that information to learn the typical behavior of players in the field. So what I want to be able to do is to learn the behavior of 4 field players for games of a given year, so that I can find out what our opponents are doing and how they developed their software over the years, so that I can compare what they did in 2 years ago and this year, etc. It's work in progress. I'm currently still working on building tools and I'm analyzing log files, and I'm studying object-oriented neural networks. So that's one of the things that I'll be talking about. And I use the turtle log files to identify game situations, team formations, and player actions. Now, learning has already been done in several other leagues, like in the Simulation League, in 3D, mostly used in low-level control or let the robots walk. In 2D, mostly tactics. And also in the small-size league, you see that tactics is a topic that is being used in machine learning. But most learning applications are concentrating on low-level learning, motor control, dribbling, shooting, stuff like that. And what I want to do is to learn the behavior of our opponents, so to be able to look at the game situation, the role that the agents are playing, what the actions they're doing, and actually finding similar situations in all the log files, so that I can use this information to find out what the typical behavior of an attacker is or a defender, and how an opponent is doing that differently from other opponents or from ourselves. And I want to learn that on a symbolic level. So the important thing is that how do you do that? And there are 2 things that are important to me. First of all, I hate football, and I don't know a lot about football. And so I went to somebody who knows a lot about football, actually the bondscoach of the Dutch futsal team, so it's soccer playing, indoor soccer playing. And I warned him about my preoccupation about football. And I said, I really dislike football. And the first thing he did is gave me a hand. And he said, futsal players actually have the same attitude. So he said to me, field football is okay, but it shouldn't be a bother to us. And so Max Jaden is the guy who gave me a lot of information about how he trains their players. And what they are using is set pieces. Really what I want to do is to be able to learn the behavior of the opponent teams and express that information in terms of futsal set pieces. So I want to generate set pieces so that I can explain what is going on. And one of the difficulties with neural networks is that they can do a lot of interesting stuff and they learn a lot, but then it becomes very difficult to find out what it is they learned. And if we want to have reliable systems, we need to know what's going on inside a network like that. So I want to be able to explain what is going on. And also, I want to learn how this works so that I can have a more basic understanding and perhaps in the future do something more about learning to play soccer. So I give you a short example of the kind of set plays that I was given. This is an attack scheme. And so he explains the kind of things that are happening, and then you'll see that there are all kinds of schemes like that. So what I want to do first is detect a pattern in which the players are playing, determine on which half of the field they're playing, find all the different variations of the similar game situations we have, and identify situation for each team player for that team. So basically what I do is I use the world model from our log files. I generate a couple of images from the game situation and then want to generate a game situation classifier and do the same thing for game situation actions. So if you look at these set pieces, one thing they have a number of formations. So here you have a 1-2-2 formation. The problem is that we have information from FIFA, from UEFA, and from KNVB, and they all use different formats for formations. So I had to invent a new one that covers all of them, but at least there are a number of different formations that are being used. And every player has a role in a formation. So we have these identifying numbers, and usually in our schemes we have the number of the robot. But what I want to be able to do is to give the role number within a formation. So a robot identity will be a number given that the robot plays within a certain formation, and these formations are dynamic. They can change during a game many different times, depends on the situation. So first thing I did is to build a set piece editor in which I can enter all these set pieces and have a visual editor that I can later use to inspect the set pieces that are being generated. Then we have a program to load the log file, and you see here at the top, let me see. There is a box where you see all the ref box situations, and then we have a start and a stop command. So the only thing we're using is actually everything from start to stop. So the things in between is positioning of the robots and people walking around or putting the ball somewhere. So only use the situations in the start. The second box you see there, I analyze all the different formations that have appeared in the log file, which is one half of a competition. And also give a percentage of how often these occur and what the average step size is, so that I can select from either the ref box or from all the formations. You see this little picture there. you see the formation is 2-0-2, which means there are 2 attackers, 0 midfielders, and 2 defenders. In futsal, they're using the notion of midfielders or wingmen. And what I show here is one of the first items there, and we draw lines between the start and end position, and then down there you can scroll through all the different steps. So here you see that the actual formations are changing, and in that situation you can browse through this thing and then have step by step see what's going on, see if there's anything going on in between. So game situations are expressed as attack or defend. The second thing is our half of their half. The third thing is, are we playing wide or are we playing small? And then we have 2 attackers, 1 midfielder and 1 defender. So one thing I can do is to find all the episodes with the same game situation, and that is the basis to find ancient game situations that are comparable, so they can look at, do I have a situation in which a defender is against 2 opponents, and then I can browse through the entire log file and find all the situations that are comparable, so that I can at least have an idea how often this particular situation happens in this log file. Here I give an example where I browse through the whole thing by roles and actually see some colors there. So the lines, like a green circle around it is a defender, and a red circle around it is an offender, but then also is a color indication for the action that they're taking, and the lines have colors, and while they move over the field, the colors track so you can see where they changed role and where they changed actions during that episodes. So I can go through this whole file and analyze all these situations. And here, with the pass, I know who gave the pass and where the pass was going to, and I can step through the whole thing and find out what did lead to this pass and what happened after the pass. So I can learn the entire episode and find out what was going on. Now, the important thing is to learn something in a network. So what I did is use all this information in a log file because we know everything that the robots did. So that's my ground truth. And that then goes into a neural network with an attention network, which is actually a sequence transformer, where we have the total game situation as input and a local picture of every of the 4 field players with their positions. And that goes into the network together with the identity. And the output of that will be then the role each player plays, the intention he has. So say, I'm going to try to go to defend, or to defend an area, or defend a line, or defend against an opponent, or any other action. So that particular network will learn things, but the inputs are not only pictures, but they're also labels, like the intention is expressed in a word. And so I want to create a combination of a network that learns both things like a normal network does and things on a symbolic level, so that I can express the whole thing in terms of futsal speak. Now from that situation, I can then generate a set piece for all the situations that I encountered, and then have a total model of the behavior of our own team. And once I have learned those behaviors, then I can take the opponent team as input and use the network to classify all the actions that they're taking. Now, if all that will work, I don't know. As I said, it's work in progress. I'm currently in the position where the first neural network is going to be built up. It's actually my third attempt, because every time when I try to build a network, I find a new article about someone who came up with something completely new that I had never heard about before. At the moment, I have about 100 articles or papers that have been written in the past few years about similar situations. And actually, I found that Disney is doing a lot of this stuff as well. So there are a lot of people in the world who are thinking about football and analysis, things like this. Another thing that I'm doing is I'm building a mini turtle with a Jetson Nano on it and a Google TPU, so that I can do some local learning, a thing called continual learning. But I want to not take too much time, so I want to close with showing this as the kind of hardware that I work with and build to do some experiments. Okay, that's what I wanted to show you. Questions? Yeah. Yeah. Okay, there are two things I intend to do about that. The first is, at the moment I have the trained network and I use it on an opponent team. I can find situation where it says, I haven't seen this before. And then I have to do something manually and say, okay, this is a new set piece, a kind of behavior that we didn't do and I haven't seen. Another thing, which is much more difficult, is to make an autoencoder that is going to classify all these situations automatically. And the kind of thing I'm hoping to do now is to first handcraft all of these labels and then later on have a basis to be able to use another network that will actually learn how to classify these and find out that there are new instances of behaviors. Okay? Yeah, I started out with, I wanted to actually not learn something, but teach it. That's why I went to the KNVB. I said, how do you teach people to play soccer? And can I use the same technology to teach our robots how to play soccer? And that's when I started with these set pieces. And I wanted to use these set pieces to actually let the robots learn. So it's not learning, but it's teaching. And I found that too difficult to actually do at this stage. So instead of that, I used these set pieces to try to learn what the behavior of our opponents is and of our own team. Our own team is the simplest because of the ground truth. Okay?
I was just thinking, very interesting. Did you also consider to do it all the way around? If you take a human football soccer game, put it in a computer, then make objects of the humans, and then put it in your archive. You can check if your set play is still valid.
Yes, well, I'm working together with people from the University of Leiden. We're doing something similar, and they do it for real soccer, and they have digitized games of the German competition over several years, and they collect all kinds of statistics so that they can actually classify the behaviors, and I'm working with them to see if what they find is they're using our log files with their analysis tool to see if they can reverse engineer and see if what they come up with is that much different than what I do. But that's certainly an option that we are considering. Yeah. Okay. Thank you. No.
It's an open question, maybe to you or maybe to other people. Do you think generative adversarial networks could be used for learning soccer strategy? I work on artificial network, but for embedded computing, and I don't know. I have no background about GANs, but it seems to be an option which could be useful. And I'm thinking about launching a PhD on that in next year. And does anyone has any experience with that?
Well, René has some experience with guns.
During my summer break at university, when the students are at home, I typically tend to take a subject that interests me and then play around. So I've played around a month or so with GANs. And the generative properties of those are really striking if you look at the recent applications. So why not train again that would be able to train the strategy that would win for this pattern? If you take the right model and you have the right data, you can do that.
I've been told that there is a problem of convergence.
It's more, as I've seen, it's more like a handcrafting than science at the moment. I think that the autoencoders are better supported by the mathematical analysis. There you can really prove the properties of the networks that you get. But in GANs, it's all like more than magic and art. And the results, especially in image processing, crazy, amazing.
I brought my computer, so anyone interested, I can give a demo offline. Thank you.
Just testing. Thank you. My name is Jurgen van Eyck. I am one of the members of the VDL Robot Sports team. We would like to give you a small update of our team of 2019. So, first I would like to introduce the team, give you the team status, and tell you about the outlook about these 4 subjects we have to handle. The team, it's an open team with 40 volunteers of, 10 kind of 10 kind of companies. It consists of team members of the old Philips, like me, but also a lot of new members, early retirements, retired, some internship students, and we have some graduation projects. We as sponsor we have VDL, ETG, and Maxim Motors, and also Boss Rex sponsored in the past. On Wednesday evenings we have the normal team evening, and we have a location in Veldhoven. We call the Robot Sports Arena, but I know another team call it another. Having a different name. Same building, by the way. And we work often together with the Dutch teams, the Falcons, the RAF, and Tech United, alphabetically order, by the way. That's what humans. So we also have some robots, and I have a small movie about 90 seconds to introduce the things out of the robots. This is 2016, the European Championship. This is something what not always goes well, so that's also part of life. So you see that we still play, but also see our big problems, like that we pass, but it is not always accurate, too slow, and that's things we have to address soon. Let's take a few minutes, 2 seconds. So this is, it was standing free, yeah? Have to deal with this situation. But sometimes it went well, and then we can have things like this, so it's possible. And here for example against Tech United, we see some very good defense because they cannot pass the ball here. So that looks well. But sometimes it works, even against the good opponents, so like this, and then we close it with it. So this is also against Tech United. That's the only one we made so far, but more to come. So the team status. On the soccer behavior, we intended to improve on the passing, shoot to the goals. But the idea was to start with machine learning. It did not start up as we tried to. On the ball pickup, we made some robustness improvements, and by adjusting the basics actually. And also we're looking into the response of the robots, the reaction time. And for that we adjusted also the architecture a little bit and the behaviors. And when we were playing this year in the Portuguese Open, we were struggling with all kinds of hardware issues, and that makes us think that, okay, whatever we do on the behavior, it does not help if the robots break down. So we pull the trigger and we go for a new hardware platform, and that's also in a few slides. And also we started in cooperation with the Fontes team to try to, if they are able to run their behavior on our robots. So that's something is ongoing. And also we also have a side effect of promoting technology, and we are able to we adapted the Snap language, which is a kind of comparable with Scratch. So you can build kind of behaviors. We attach it to the robots. And we have now a setup with the demo field which we borrow from the Falcons. A setup where we are able to run with 4 teams, and every team using a corner, where they have to do an assignment like driving with the robot around the objects toward the ball, and they can do it on 4 times on the same. And they have to think about it how to do this. So they have to make a plan to program it, test, improve it, and then they found competing to 4 teams and see which takes the best solution. And we have some examples. So we did it at a middle school as part of the 100 years celebration. And here we cut the field, and here you see indeed the tables of the teams, and put the ball in the middle, and then start together. And you see that sometimes you really do it at the same time, so they really collide. But it's really nice to see that this is people about 12 to 15 years old, that they can do it. So we thought, that's nice. Let's try to do again on the Maker Faire, and then we have to do it, and we combine it with demonstrations. This the Maker Faire is a fair for maker industry, a hobby kind of things, and also promoting the technology. And there, these guys start to play with our robots. It was sometimes scary because we limit the robots with the speed and the possibilities, but they really start to program themselves, making all kinds of things. Like, it's very basics, but it gives already the not only seeing the robot playing, but also play with the robots, and that's really a nice part. So that brings us to the outlook. That's because we need some team members. So we are limited on people and budget. We also think that we are hitting the ceiling with the current things to make the next step. Big step, actually. We make steps, but small steps. So we're looking into how to update things like the vision and the motion with the learn from the others, like how do you do obstacle filtering, learning. But also we need to bring the cost down. So we're looking forward in the future to not having a dedicated building hired, but maybe think about a sport hall or a football field, futsal. And also, going to a tournament is a very expensive thing, especially the transport cost for the robots. It's really, yeah. So that's also taken into account for the new platform. One of the main things to improve. And yeah, we also we want to increase the speed of learning, and for that, for all what you learn, you need a kind of simulator. So we're really looking forward to the MSL simulator. And also we chose to work together with the Fontes to look if they can use our robots to play around it, and then also there will be a cooperation, good or bad, maybe practicing. We have the regular practicing against Falcons, and so that brings us to these commands, and yeah, that's what you have to do: set, update, and upgrade. That's as simple as that. Yeah. Yeah. So that brings us to a kind of revolution, not of an evolution. So our current platform is. We can play with solid, but it also has some side effects. So we made new robots, and we currently are in the construction phase. So we design the platform. Some guys also think about what kind of choices. So we choose also for 4 wheels. And it's mainly because of the speed and also the stability. They improve the ball handler part, so where the ball handler is in, and the kicker, and also think about the wheels. It's independent suspension. This is an artistic expression of it, and one of the key features is that this robot must be fit into normal suitcases, which can be used taken into the plane. So we don't want to send the robots 4 weeks before in a crate to all the nice places where RoboCup ends, but we put it in the suitcase, and then some 4 or 8 extra suitcases, and the robots are the other side of the world, or in Portugal or whatever. So this is the thing we're currently working on, and we expect that this robot will be working in the spring tournament and also at the World Cup in France. The frame is new, bulk ball handler, and also we updated with the electronics. And also, for example, we're looking into an update of the Kinect, so we are looking into the Intel RealSense hardware as a replacement of the Kinect, which is a very small device. Automotive vision, we started a cooperation with a hardware supplier, and that's we want to try the vision of this automotive industry to apply it on our robots. It's also bringing us to the future generation. So it was originally planned to start to work on this one, but due to these, we have to put it on hold due to the team revision. So this is the big upgrade. We have some experiments with the hoverboard environment. We still continued and probably will pick it up after we finish the original platform. The MSL simulator, on that one we changed the scope by trying together with Fontes to give them the opportunity to run their robots, of their software on our robots. We had a joint team at Portugal based on to give them the experience about RoboCup and us to go with less people because we're stuck in all kinds of appointments at home. And the next step will be, if it's running, is using each other's simulator. And also about the football and indoor fields, the basic constraint for that is having a robot which not damage that hired location. And for that we need the two wheels robot first, because that has can handle the floors over there. It's a very small update, but so far the update from our team. If there are any questions, and maybe you can answer them. Oh, René.
Building robots on one hand.
Yeah.
But is that the only part that forms the ceiling? Or
No, the ceiling is more the behavior and the perception of we.
How do you perceive that ceiling? So, can you be more specific?
We see that the progress we make in, let's say, 6 months.
So which progress would you need?
Now I think the number of goals. That's I think that's.
Okay, that's very integrated.
No, but that also means that you see that we slowly progressing in improving our game. So if we play regular against the Falcons, you see that we still ending up with the low-level things instead of starting with the learning phase. So we are still tweaking and making small steps instead of jumping into the next level.
So where do you see this jump to the next level? What should change in order to make that step? I'm not saying that you can just do that, but can you define what you would need to do?
Yes. We still apply a very basic kind of behaviors. So we can have problems to adjust. We've promised to raise the setups quickly. We're not making that steps to get attached to the top teams. So we're lagging behind, and we should come closer. We slightly come closer, but you want to come closer and overtake.
So what is lacking? Passing that's not working. Is it
Passing, for example, is not good. Picking up the ball is poor.
But what would make the step change for you? If I could do this, then this.
I think if you can pick up the ball next to each other in a second and shoot to the next player.
So would that be in principle possible with the current platform?
It will be, if the new revision, it will be possible. The hardware will but the development speed and the steps towards the next things are limiting ourselves. So we need to find a way to make faster progress.
So I was also wondering if with respect to the things that you mentioned, can you make use of things that already exist?
Yeah, but you look at that is one of the slides here, I think. Let's see. So here it's clearly try to reuse the good examples of things done. So, for example, I think obstacle filtering is a very. I think it's from you and from Kabada. We looked in both solutions, and we select our own parts of it. No, but it will help to find where is the ball. So before you can intercept, you need to know where it is. That's one of the example. That's not the example of picking up the ball faster. We see that we try to every time manually adjust it, the skills. Why not try to learn it? So that's the low-level AI. But we don't apply it yet. Yeah.
Okay, we can have this.
Yeah. No, you don't. You might not need it.
I was just looking where you would like to put your focus in order to make that bigger step. And if there are other teams who already are doing this, to see how you can actually quickly adopt that. So if you have already few people,
yeah, that's
be very picky on where you put your effort.
Yeah, and that's.
Use the parts that are working for others.
Yeah, but there are also a lot of that's what we prefer. But also you jump in there into kind of things like, for example, every team has its own behaviors adapted to its platform. So taking it over takes also a lot of effort to adjust it to your situation. I think it's a very tough challenge to learn to use each other's vision system. Just the vision processing, not the camera, and then using it. That will be already, I think, quite a step for all the teams. Because you also see, if you look to that's maybe looking back, in 2006 there were 36 MSL teams. Currently, we are lucky if we have 8.
I think there are still 36 MSL teams, and even many more teams that do competitions that are much like MSL. There are 100 teams in India.
Yeah.
And there are worldwide, I think there are tens of teams, but they cannot make it all to the same place at the same time.
Yeah, and you also know that if you go into a competition, that the best way to learn and make progress, because wherever you think in your laboratory, you think about how it works, and you have the idea, and you think it's look like this, and then you come on the tournament, and the first thing you find out is that these opponents, these nice guys, find a trick to counter you, and you're running into the issues they caused by their change. In 2004, we had a very quick path. 2002, we were the guys who go shoot as fast as possible as the first team, and we go into Japan, and we were like, yes, let's go. And then we found out in 5 weeks they all invented defenders, and they're putting the robots between our robots and the goal, and we could not make goals anymore because they started defending.
At some point, you have to bring the movies from that time, because that would be really enjoyable.
I think I have a few on my laptop. Yes?
Thank you very much. Right now we'll take a short 5-minute break, and after that we will continue with our guest speaker.
Als jullie twee vandaag een rondje gaan maken, jullie hebben die hardware en jullie hebben die idee over de software en hoe je dat moet bouwen. Want eigenlijk, je wilt er gewoon, je wilt inderdaad wat jij zegt, je wil op dat toernooi zijn. Ja, dat is wel belangrijk. Maar dan moet je dus wel heel duidelijk zeggen, dan gaan we dit en dit en dit en dit doen samen en dan zijn we op het toernooi. Dus dan moet je heel erg focussen.
hoe moeilijk het is als een jong team, hè? Want je hebt het ook ooit gehad. En dan als een nieuw team begint, dan heb je een loop tegenaan dat in de huidige top.
Ja, nee, dus je doel moet zijn van op het toernooi komen. En aan het spelen komen, aan meedoen. Ja, gewoon op meedoen. Al heb je maar 2 robots bij je, maar...
Ik ben het helemaal met je eens, alleen wat je bij ons in het team ziet, je ziet het ook in de resultaten.
Wij geen verwijt, hè. Dus van, ja, wij willen natuurlijk zoveel mogelijk teams inderdaad, wat je zegt, op dat...
Die uitdaging heb wij destijds ook opgepakt. Wij willen ook voetbal.
Zij kunnen wel die soort 5 K's in de lucht krijgen, hè.
Nee, maar dat werkt samen. Maar wat je eigenlijk wil,
van een joint.
wat je zou willen, wat heel moeilijk is, een standaardplat komen. Als ik daar als kilometer in koop, dan zet je een standaardplat op en ik pak de software van.
Ja, dat was het hele idee. Nou, dat is met Tulpen 5K nog niet helemaal gelukt, maar het idee was goed. Maar eigenlijk zou je willen dat je gewoon als startend team een platform komt met 5 robotjes die gewoon in ieder geval als je op start drukt al gaan voetballen.
Ja,
als base.
Aan de andere kant wil ik voorkomen dat je 50k robot is. Dat is allemaal
kijk, in principe...
waarom teams lastig zijn, weet je, dat is de reden. Eerst langs de universiteit, die zegt tegen schoolbestuur van, nou, wil je meedoen? Ja, wat kost dat? En je zegt, nou...
Dat is 5000 per robot.
En je zegt, ja, ik heb weer 70.000 € nodig. En wat doe je dan? Ja, dan hebben we er staan. Dat is een lastig verhaal, denk ik.
Op zich zie je, maar wat ik zie is, wij hebben financiering voor een project krijgen. Hoe is het altijd eigenlijk een vrijwilligersorganisatie doen, dat moet ook professioneel geleid worden. En wat bij ons ontbreekt is een systematisering benadering. Die hebben we nou wel ontwikkeld.
Een paar weken geleden waren er een paar van jullie waren met een smartphone geweest. Ja. En eerst week tegen jullie zeggen, ja leuk, dat doe ik. Dat zeg wel eens, maar dat zijn 5 jaar mee gekomen. Dus als je dan denkt, oh 5 jaar, oké.
Ja, maar dat is wel echt wat jij zegt, dat is wel echt een voorwaarde.
Daar zie ik ook de meerwaarde voor.
Dat wordt natuurlijk onderschat, hè, ook voor de buitenwereld. Ja, dit is gewoon echt spanning. Helemaal nooit kunnen krijgen. Maar daarom denk ik dat die van jullie, dat daar eigenlijk dat jullie heel complementair zijn in bepaalde opzichten. Dat hadden wij ook bedacht. Dus ik vind het superleuk om te zien dat jullie dat al een keer hebben gedaan.
Ja, we zijn bezig.
Want dat is jullie beide weg naar de toernooi. Ja, welke betekent ik geloof het niet.
Nee,
Well, for me, the last one in a row of a lot of speakers. I'm afraid I'm going to be a lot less technical than all the people who have presented until now. But our goal is kind of a little bit different, in some ways the same. We are busy with actually how can we let children in a wheelchair play soccer. And the project started a couple of years ago, and we started out with the technology of the TUE and said, can we use the turtle technology to build like a simple robot and let these kids play soccer, and I'll tell you how it went. I'm going to have a little talk about the why did I start. Well, what is the product actually? I see that there is the old index in my brainstorms, in my... it's of the old, it's the wrong index, so I'll just go out. Okay, myself, I'm an industrial design engineer, and my approach is kind of the other way around. I start with the user, and I look at what does the user want, and how can I facilitate their problem. And for me, I'm already 15 years designing products for people with a disability, and the last 8 years it's for children with a disability, and it's all about let them participate in society. And while I was doing different kind of product, like little parks where you can play within the community, you have these little, in all the different areas in the city, you know, you have these a slide and a swing and stuff like that. And there I designed one, how can you have children with and without a disability play together, and how should the playing field look like. And there I met Elina. Elina was a girl who couldn't talk, who couldn't sit, who couldn't eat herself, and she had like really had to struggle to have interaction with the world. And she had this little machine that was an automatic bubble blower, and she had a big button, and because she was also very spastic, and then she could like press the big button, there would come a lot of bubbles and it would float by, and then we said, oh, Elina, what nice bubbles, and then, you know, she would all light up, and then, I have, you know, I can choose to make some interaction, and that's my only tool. So the first thing I said, well, I can, we all have spare time. I said, what are simple tools so that, you know, she could use a button for something else to have interaction. So the first thing I said, well, there are electrified water pistols, so I'll just convert one, and then she could have a water pistol fight. And, you know, at the age of 6, she could have the first water pistol fight with her brother and her family, where she could actually shoot herself. And the nice part about it, that she could also keep shooting while her brother didn't want to play anymore. It was the first time she could actually be naughty, you know? And the brother was completely surprised, like, but Elina, what are you doing now? You know, like, this is not possible. And she's like, yeah, I'm just, you know, you fill up the tank of the water pistol, and I keep firing. And there it started. Okay, well, you know, she was at the moment also training to learn to drive in an electric wheelchair, and because of her very bad motor skills, she had to like hit the accelerator with her right foot that was kind of working, and then use her head to go left and right. And she was already training for 1.5 years, and kind of the fun of trying to learn to drive this wheelchair was kind of, you know, getting lost. And I said, well, maybe she needs something to really interact. And at the moment I was designing the Amiga robot for the TUE, was giving him his appearance that he has now. And I was working together with Heiko, and I said, well, you have these automatic soccer robots. Don't you have an old one? No, you're in number 5. I'll have a number 4, and I'll just, you know, screw it in front of the wheelchair, and then she can play soccer, and she has a reason to drive around and go places. And then Heike says, well, I would, of course, you know, be happy to facilitate you, but the kind of 2 problems. 1, it's the 25,000 euro, so it's kind of an expensive robot, and 2, it can only drive actually on a very level floor. So it's not really useful. So then I had a look around, how much Elinas are there actually, and why don't we start up a project to actually, you know, build a very simple soccer robot to have people like Elina who are in a wheelchair play soccer. I know what it is. Is this how it starts? This is the movie of the latest test, we started out with just building a proof of principle, and then see, how much enthusiasm they have with using it. And here, these are just some, skills like what is going good, what is going wrong, to see how far we have to go from this kind of proof of principle robot to an actually robot that we can use. And you see how much pleasure they already have with a soccer robot that's still quite poorly in, the shot, the holding on to the ball, and stuff like that. I must say we yeah. Okay. Yeah. And in like in a small version, we have the problems you are having. We had our. Where's the laser? Yeah. We put quite some work in this ball dampening system to prevent the ball from bouncing back out. Actually, we have two dampening systems. These are kind of an iteration of the Festo fingers. If you deform them, then they go round, and that's how you pick stuff up. And we do it the other way. So if you shoot in the system, it closes, and then the fingers deform, taking energy out of the ball. And we also have. I'll explain that actually later. What can we do at the moment? It does catch automatically. We want to be able to hook it up to any wheelchair, which is also a big challenge because there are a lot of different wheelchairs, and so you have different places where you want to hook it up. We want to be able that they can participate in the neighborhood, so then we're going to have a surface area where we drive around, which is actually not so level at all. We can say at least the street or the sideway, but still, everything's going to bounce a little more. And we actually want to build a new sport around it. For them, what we accomplish for them is a new sport. They can actually sport. A lot of these kids have diseases that are progressing. So as they get older, they also get worse. So with a sport like this, you can always be a top player, because actually, as long as you can drive around and you can push the button for shooting, you can play this sport. So you're gonna, do your team sport, feel included. One of the problems these kids have is building friendships, especially as they get older. They have difficulties to kind of keep up with their fellow kids, And if you're a teenager, well, you're not on your best behavior, and they kind of, lose their friends, and they fall back on their family. And that's also why, I would really like to bring this sport, especially to the niche group that are driving in an electric wheelchair. They have severe problems of loneliness. Well, if you play soccer or play any sport, you win, you lose, you have a lot of enthusiasm. With soccer, it's also a game. There's a lot of talk about soccer. You watch the game and then a lot of talk. So if you also play the game, you have more interaction with, well, I'm a right-wing player, and I scored last weekend. And here you see that even within the disability class, that the kids in a wheelchair, they are located here in persons with a motoric limitation. Only 23% of them actually play a sport. And here we say people without a disability have about 60%. So there's a big gap. And one of the reasons why there is a big gap, there are not that many sports. So you only can choose a few sports, and if you don't like them, well, you kind of have a problem, and especially if you're in an electric wheelchair, you have like two sports, either you like hockey or you don't like hockey, and we have jeu de boule. And that is, well, okay. So, yeah. Here we have like two dampening systems. So here we have the Festo fingers. And our, like what we have is kind of the same as the other solenoid system. So we have here the big capacitor. We have the charge pump that pumps up the battery to the voltage we need in the capacitor. We are driving now on an Arduino because we don't need all the calculation power you need for if you're really an autonomous robot. We use some ultrasound sensors to sense the ball, and we have a little motor that's also run by the Arduino, so when the ball has been seen, it closes. Well, this is our control. So we have an amount of bars that lit up that you know at which speed I'm gonna shoot. Here we have a little button which you can adjust. Well, this is the firing button. We designed like two ways of controlling. One is that you kind of set your shot speed and then shoot, and the other one is that the longer you hold the button, the more it will charge up, and if you let the button go, it will shoot. And last but not least, very important, is that it needs to be used with external components. So they mostly have specialized buttons, or if they have less finger function, they have very little micro switches. If you can plug that into your system, you know, they can use their normal ways of operating to play the sport. Now this is the catching system. You know, it sees the ball. When it's close enough within range, it will close the hoop. And here we have the doubling dampening system. So this is the one. There's a spring behind it also, and we have the Festo fingers. And this is just what we did to have kind of a proof of concept. We actually want to go to a place where you can actually take the ball away, you know, and then actually have a more kind of a soccer play. Until now we had two prototypes. We had reached it with the target group, the parents. We had a lot of enthusiasm in the group. In the schools, they were very enthusiastic to like help us build the sport. But one of the hard parts for us is if we want to sell it at a consumer level, you know, it would be around the cost price of 900 euros. So that means that the production price would be around 300 euros. And that's the thing where we're struggling now. We're using components that, you know, we are around the 2,000 euro robot now. You know, we made some progress and say, well, we can drop to 400, 500 euro robot. We think we can drop more. But that's actually why I'm also here. For us, it would be really beneficial if we could have a look at your design and see the progress you already made about the ball handling, the solenoids you're using, how you're actually actuating the solenoids. We also had the problem, we had a very small team. We had a robot that had been built. It had been like in the cupboard for half a year. And then there were new guys working on it. And then, you know, the hardware broke down and we had a lot of problems fixing it. You know, it kept breaking down and you don't know why. And then, you know, it takes a long time to learn again. And then now the new team has all the old knowledge again. And oh, we know why it broke down. We fixed everything. And that's also what you see in the testing, because we had a grant for a feasibility study. We really needed to keep it working, so you know we powered it down, that we were sure that it wouldn't burn out during the testing. But you know we did actually get a much better shot, but with this testing we kind of, you know, played it safe. So that's, you know, now we're in a position where we can upgrade everything again, and but we want to not like improve our design now. We want to give it a complete overhaul. So therefore I'm also busy trying to get a big grant, and you know that we can do the work that is needed to get this kind of prototype into a real production product. So if you you would really help us out with your knowledge, and that's kind of, you know, what are you using as a dampening system, shooting system. I thought the railgun was really nice. We had a look at it, but we thought it was like so much work, we're gonna never make it, and probably also gonna be very expensive. But well, I'd love to have a chat and learn more about it, but that's from all the team. So if you're willing to share your information with me, have some ideas about it, well, I'm also here for dinner. let's have a chat and let's exchange some email contacts, and then well, we'll keep you posted how it goes. Okay, thanks.
This device, yeah, robot, and non-handicapped children. Is it safe for the non-handicapped children to play with the people that are handicapped that are playing with the software?
Well, at the moment it's not safe enough. So we only use it in testing environments, and that's why we also have well, it will be a dinner again, but we have a graduation student for the safety, because in theory it shouldn't be able to shoot when there's no ball, but you see that in reality sometimes there is, it does shoot. So, but we knew this is just kind of a proof of principle prototype. So we really need to improve the safety system. That you're sure that if the kids are in the neighborhood of the system, they're not going to shoot. Especially because if you're designing kids' toys or play parks, it's okay for the kids to kind of get hurt if they can make a calculation of what they're doing is very risky. So a kid knows if it's 2 meters high and it's going to jump down, it's probably going to hurt. But if you're going to put the soccer ball into the robot, which they were doing the testing, and they always do it like this, but of course there's an off chance they would push it like this in. The system would shoot and you would break a couple of bones. That's you're out of business. So we have a lot of focus now on what do we need for a safety system, how can we make it safer, also how can we do the ball handling better, and I think there's a lot of information about it, but there's still a lot of work to do, especially in the safety side.
Yeah, first of all, thank you for your presentation, and it was really nice to watch, very inspiring, let's say. And just to tell, we are just, back in Portugal in our lab, we are just starting a second phase of a project called Intel Wheels, which of course has nothing to do with playing sports with wheelchair, but it has a lot to do with using wheelchairs by people with high degree of disabilities. So the main focus is on developing general purpose interfaces for users that can be adapted for driving a wheelchair. So we are using things as simple as you described, buttons, something to push, using the head, using brain interface, for instance. Okay, and also dealing that together, or making the wheelchair more, let's say, space aware, looking particularly to the safety. But safety is not this particular case of safety, but also safety regarding dribbling around or falling out because there is a step or stuff like that, or going against an obstacle. So I think there's a lot of linking points between the kind of stuff we are going to work in and the stuff that you're doing here, because when we talk about safety, you have to look at it in a broad way, of course. And you described very well the problem of putting the ball there. Of course, but and depending on the speed of the wheel, if you crash against another wheelchair, for instance, and it.
Well, we already had our crashes with the robot. Is because now it's like half a meter, extending the wheelchair.
Yeah.
They don't kind of know it, and we had one of the guys was actually tilted a bit backwards.
Exactly.
And then he could hardly see the tip of our robot. And then he was like maneuvering next to a wall. Oh wait, I'm gonna turn this. Sorry, all the parts. But also on the other side was that there was one of the test subjects was like, oh, where's the football? Oh, the football is the goal. Oh, I'll get it for you. So he drove into the goal and missed that there was a big metal bar on the backside. He miscalculated how far he should drive, and our whole front end folded in. But thank God it was quite flexible, and a little duct tape, you know. But that is really interesting, you know. And also the problem with the wheelchair, it's your legs. If you're in a wheelchair, you're talking about somebody's legs, and if we break it, you know, if they run into the wall with the soccer robot and we destroy the battery pack, they're going to be without their legs for, at least in Holland, it's going to take, you know, if you're lucky, 6 weeks. So either you're back in your bed or you're in like your push wheelchair. So also that we're thinking about, well, how do we do the connection with, you know, the wheelchair? Do we need a safety zone between the soccer robot and the wheelchair, like a crumpling zone? Or, you know, now with the big grant, we're also looking, maybe we want to detach the robot altogether. It will drive itself. It just has two proximity sensors, and it will keep like a train in front of your wheelchair, you know. And then we don't have the possibility of transferring that energy back into the wheelchair. So there's a lot of things to consider if you're messing around with the wheelchair. And first we thought, well, we use the battery of the wheelchair. That's how we started. We just opened up the wheelchair, you know, hooked it up directly to the battery. But the thing is, if you make a mistake and we would, you know, feed charge back into the battery, it will go into the electronics of the wheelchair. Yeah, if you fry the wheelchair, you know, it's a serious problem. So, and while testing, you know, we found out that actually with a battery we had more than enough power. So we started out with the wheelchair, and then we have to plug into the system, and then we need an extra safety system, so we make sure that, you know, we don't give feedback into the electrical system of the wheelchair. So now it looks more and more that because the parts are actually quite cheap to make it autonomous, you know, how far can we go? And then you can protect the wheelchair better. It's easy to implement. You don't need any, you know, special adapters, specialized companies that build your adapters or, you know, certificate your robot that is allowed to use with that wheelchair. So that are a lot of the interesting things to talk about. But I really would, keep in contact what you're doing, what we are doing, and there's definitely overlap.
Yeah? Maybe a stupid follow-up question, but how do you know how the kids feel about improving the safety? Because me as a kid, I liked it. If I would climb into a tree and it was completely safe, then it would be boring for me.
Well, the thing is
kids like it too, when it's a little bit, not dangerous.
Well, the thing is that it's allowed to, like, shoot the kid that's standing right in front of your soccer robot.
Mm-hmm.
You know, like half a meter, you shoot full out, and it would be really nice if the other person would say, ow.
Yeah.
Because then that's right, you shouldn't stand in front of my shooter, because I'm shooting powerful.
Yeah.
And that is, you know, perfectly okay. But if you have like a little girl and she's, all right, well, put the ball in, you're going to shoot. Now this is a nice game, you know. And then she kind of puts her hands in between, and due to a malfunction, or we didn't anticipate that she would do something like this, so we didn't build a safety system that would, you know, then you would crush your hand, you know, and the damage to the kid would be so severe that she couldn't anticipate that because she was putting the ball inside the robot, that she was actually taking a big risk.
Yeah, I was meaning more with specifically to protecting the wheelchair.
Well, the thing with the kids in wheelchairs is, you know, they really need their legs. So I don't think they would appreciate it if they would be able to take a risk to break it down.
Okay.
And because if it breaks down, it's also a lot of hassle. You know, I know, of course, some parents with kids in wheelchairs, and if your electric wheelchair runs out of a battery in a forest,
you're in for a seriously sporting game. You have to unlock the motors and then start pushing. And it's like, you're drenched in sweat when you're out of the forest because it's terrible.
Also for Marta is you also have to put it in perspective.
Yeah.
Okay, because if you were not able to climb a tree at all, then climbing a tree, even knowing that it's safe,
yeah,
would be thrilling.
I was just wondering how the kids would feel about that. I don't know, maybe if it was asked like, do you want to have a protection?
The example of the shooting, the water shooting is a good example.
No, I can understand it, but I was just wondering.
Yeah. Okay.
How the kids feel about it.
Well, the kids felt about it that all the kids said because the shot
everything
was
that
actually
enables you to do something that you otherwise you can do. Of course, they feel thrilled about that.
Okay.
I'm quite sure about that.
I don't know. Okay.
Yeah.
Sure.
I think you're running into problems with interaction of humans, which is the MSL is not having yet. If when we looking forward and we're going to play with humans, with the robots, we will jump into things you described now. So I think we will learn from you as well.
Well, that would be super. Well, I must say that when I saw the presentation of the font is that you can also find, if you want to make it safe, you can have two options. One, is it a ball, yes or no? Or two, is it a human? And you can mix them, of course. And like you showed finding the human, if it's walking, and then you say, oh, well, but it's a complete human. And then you can see, oh, it's approaching, and now we know it's very close, although we maybe not even recognize it as a human anymore. The robot knows where, it stayed somewhere, and I cannot see it anymore, so probably it's very close. Maybe then I can switch to a model for hands and fingers, and then I can see, oh wait, it's really close, we're going to switch. Where's the hand? Where's the hand? And then it will know in a certain way that there's a hand, there's motion towards the robot, we can give feedback on the robot itself, it will just go red, or too close or whatever, there are a lot of ways to give feedback, but there are different ways of doing it, and we can also do it the other way around. Is there a ball, and have a very precise shape of the ball, and if there's a ball there with the hand on top of it, it isn't, the right distance of all the sensors, so then you cannot shoot. But it's, I found that part really interesting. You can also look at it, like humans do. You see, that's a person is coming closer. Now we have to pay attention. If you get really close, is that going good? Is it going? And that was so that.
What we learned in that way we take the assumption that humans can do better than robots can, and we let our colleagues guesstimate what people in real action should do.
Yeah.
And they were very bad in guesstimating what will happen in particular situations.
Okay.
So we think that robots don't do better.
Yeah.
So there's also a warning from that perspective.
Yeah. Well, it's now for Andreas now it's like choosing, making some choice in safety system, and then thinking how that would progress. And of course we'll have the same trajectory as you all. We're going to think of something, we're going to test it, and then we're going to discover holes in it, and then we're going to have to improve it. But we would like to, it is designed for a sport, so it would be wheelchair against wheelchair. So we wouldn't have the safety issues. But it's unavoidable that the kid brothers and kids who are going to walk around are going to play with them, because it's an empowering tool. Everybody wants to press the button. Like the kid who was in the wheelchair, his brother who was okay said, why can't you go in your push wheelchair? I want to drive around and play with your nice toy. You see, and that's really nice, it's really empowering, and now a wheelchair is something, because I have a wheelchair, I have this cool gadget, And, but everybody wants to play with it and play with you, which is exactly what we want. But then you have to anticipate the behavior where it was not designed for. But you cannot say, well, it was designed for the sport. Well,
And now, you know, you're playing with your kid's system, we didn't think about that. You know, that's kind of a little, you're not going to sell that, you know, it's at least I don't want to have a product that doesn't anticipate at least such stuff that is quite big.
Thank you very much.
Yeah, thank you.
You like that,
yeah.
I have a little present for you.
Oh, okay.
As a thank you for your speech. It's from Van Delft, I don't know if you know. They make a special kind of paper.
Oh, okay.
This time of year.
Oh, nice. Oh, okay, thanks.
Thank you very much. Now I'll give you a short introduction of what we're going to do tomorrow. We start at 9 a.m. We'll divide people over the day in different sessions. We have 4 non-programming sessions and 2 programming sessions. There's a little bit of more information in the introduction document that we've sent you. The sessions will include new teams, how to recruit them to the MSL competition and how to help them. Inter-team collaboration, how we can help each other as teams within the MSL League. The roadmap pre-discussion, a pre-discussion for what's going to be discussed on Sunday. And the 4th one is inter-team robot communication procedure session, which is a very long session name. But it's about how we as teams can collaborate using our robots on the field. So how different teams can play together on one team using different robots. So right now I'll give the word to Wouter, who is going to be talking a little bit about the program of tonight and how we're going to arrange that.